All right, well, I'm just gonna share my screen here and hope that nothing crashes. Looks like that's working, I think. Okay, well, MOPS 102. This is going to be a lot of content. Hopefully it won't go over as long as last time, but there's a lot to go over, so I'm just gonna jump right in. The first thing that we're going to go over is some of the more advanced modifiers. So we had done a lot of the core MOPS nodes before, things like transform and noise and things like that. And now we're going to do some of the trickier stuff. So the one that I want to open up with is one that solves a pretty common motion design problem in Houdini, and that's moving along a curve, moving objects along any kind of curve. And the node that we have for that is called the MOPS move along spline modifier. So I'm just going to start with the usual peg head, and then I'll run it through MOPS convert to just quickly make it into a packed primitive, or you could use the pack SOP. Like I was trying to explain before, there's a million different ways you can do these things, and you're not required to use MOPS to do them. It'll work with any packed primitive with an ID attribute. But convert automatically does this for us, so it's just an easy one to have around. And I am going to make just some arbitrary curve for this thing to run along. So just this, whatever. It really doesn't matter. So now that I have a curve, what I'm going to do is drop down the MOPS move along spline modifier. You can see that there's three different ones. These two, the distribute and snap group, are just presets. So basically, if you know that you quickly want to make a move along spline setup where you want all of the copies that you're instancing to be evenly distributed along all curves, you can use that as a preset. Snap group will basically take a whole cloud of objects and just treat them as a single object when moving along the spline. It's totally up to you how you want to do it. But for now, let's just start with the basic one, and this doesn't apply any presets at all. So the curve is going to go in the second input, and the convert is going to go to the first one, the things that you actually want to move along the spline. And the other thing that I need to do for this is I don't want this to be a Bezier. I can set it to NURBS, and now it should work, but it doesn't really know how to interpolate Beziers very well. So polygon curves are also totally fine. If you want, you can run a resample, and that's a good way of taking a polygon curve and making sure that it's going to be properly smooth and everything. Just don't use Beziers, and I know that that's the default for the new curve SOP so in 19, so I feel like I got to mention it. So the way that this modifier works is it's sort of there's two stages. There's an attach stage and there's an animate stage. And the attach stage is basically saying, from this point, how do I want to determine what my start point for each of these things is? Because we're working in procedural space here. So like every single frame is self-contained. You don't automatically necessarily know like what your starting conditions are, because this isn't necessarily a simulation. It can run as one, but in this case, it's procedural. So when you look at the attach tab here, you've got a curve select mode where you can select, which curve do I want to attach to? We only have one here, so it really doesn't matter. We're just assigning to primitive number 0. The attach method is more important here when we've only got one curve. And what this is basically saying, where do you want your starting point along this curve for each primitive to be? Right now we have it set to nearest point. And so if I were to go here and move this peg around, just translate it in different directions, you can see that it's basically finding the nearest point on the spline and just snapping it to that position. You can also use attributes to do this. So I'm just going to copy this setup and paste it here. And now I'm going to go over here, and instead of the attach method nearest point, let's pick an attribute. And I don't currently have one. It's looking for some attribute called goal U. And so if I just want to sort of test this, one easy way to do this is just with MOPS plane fall off. You could also use a point wrangle. This one just already has a slider built in for you. I'm just going to call this goal U as the fall off attribute. And now I can set this to be, to slide it along. And you can see that what it's doing is sort of just using that attribute to pick where it wants to be along the curve. And that's just, it's looking for parametric coordinates. So 0 to 1 along the entire length of the spline. So that's the other way that you can, per primitive, you could decide where you want these things to be anchored. I'm just going to copy this setup again real quick. Just going to keep going through the different ways that you can sort of approach this. Okay. Just 1 second. So this time, instead of just copying this in directly, let's make a bunch of them so we can see how it works with multiple instances. So I'm just going to pop this in here, maybe turn the global transform down a little bit. And I've just got the default grid of about 25 pig heads. What I'm going to do now is pipe them into the, I'm just going to delete this, is pipe this into the move along spline modifier. And by default, what they're all going to do is just, because I have this set to attribute, let's just set this to the nearest point, is they're all going to find the nearest point and then just stick to it. And that's sort of, you know, this is the expected behavior from the beginning, is they're just going to find the nearest point on the curve and then snap to it. But we have other options. We can say instead distribute. And now we're going to get them evenly distributed along the entire length of the curve as the starting conditions for it. So let's actually play around with, because I want to kind of explain why this is done in 2 stages and sort of what that actually means. If I drop down a MOPs randomize after the fact, and let's randomize position and orientation both. I'm just going to set like a minimum translate of maybe 1 unit and a maximum of 1 unit so that they're offset from that curve. And let's template this so we can see where the curve is actually supposed to be. And then let's also randomize orientation. Now I'm going to drop down another MOPs move along spline. And this is not necessarily how you would always use it. You don't usually need 2, but in this case, I'm trying to sort of establish offsets and then show you sort of what this snap means. That'll make more sense in a second. So now I'm running another move along spline, and you can see that they immediately snap back onto the curve and they're oriented in the direction of the curve. The reason for this is that by default, under the offset tab here, maintain offset and maintain orient offset are both set to 0. If I crank this up to 1, what it's doing is essentially saying, I want you to snap to the nearest point on the curve, but I want you to maintain your current distance. And that might sound a little confusing. So there's a thing here called visualize offset, which is basically going to just draw these little yellow markers that sort of show you where on the curve it's attached to. When you maintain the offset and you're sort of attaching these things to the curve, what it's going to do is act as if the point on the curve is an anchor, as if it's got a stick attached to it. And so when these things move along the curve, they're going to move as if they're pivoting from that point on the curve. So as the curve twists and rotates, they'll follow as if they're stuck to it literally by like a stick. It's almost like a constraint or a parent-child relationship. And maintain orient offset is essentially the same, but what it's going to do is, because those things were randomized up front, if you want to keep that input orientation, you have this sort of slider to decide how much of that offset you want to maintain. You also have ramps that you can use to control this sort of over the length of the curve. So if I want these things to be offset more on one side than the other, if I'm trying to make like a funnel, I can do that this way. And now they maintain their offset at the beginning of the curve, but as they approach the end, they get sucked in. And you have similar controls for the orient offset ramp. Just 1 second, please. Okay, so now let's make up a quick setup that's going to use multiple curves. I'm going to make like a funnel shape here. So I'm going to make a line and I'm going to move it slightly off center. And then let's resample it. This should be plenty by default. And then I'm going to use one of my favorite nodes, guide process bend, to bend this curve to just make it like I'm going to make one part of a funnel shape, and then we'll copy this around. So I'm going to bend this, the mode when it's by default is bend in root direction. I'm going to set this to axis constant, and this just means that I get to tell this thing what axis I want it to bend over. And by default, it's -z. And then let's just crank the angle to 75. And so now I have this bent curve that's sort of facing outwards. What I'm going to do now is just copy and transform, not copy to points. And then let's make, let's say 8 or so. And then we'll do it at 45-degree angles. So we have this sort of evenly distributed funnel of curves. And if you look at the point order here, it's going up as on the way out, and I want the objects to be going down. So I'm just going to quickly put down a reverse SOP. And the reverse basically just, it's going to change which point is 0 and which point is 1 parametrically on each of these curves. So now things, when I animate them, they're going to want to go from 0 to 1. So now they'll funnel downwards. And so now let's just do the same. Let's start with some pig heads, and we'll use the MOPs instancer. And maybe for starters, I could instance them directly to the result of those splines. Actually, you know what? I don't even need to do that. It doesn't matter because I'm just going to have them distributed anyways. So spline, and we can go to the distribute tab to activate the preset. This is a good way to show off kind of what that does. So you can see that now it's saying use nearest and distribute, but what I'm actually going to do is distribute on curve select mode as well. So now I'm going to get just an even distribution of these peg heads on each of the splines. And let's go to the global transform on the instancer here and turn the scale down so it's a little bit more reasonable. And so now what I've got is these things evenly distributed along each of these curves, you know, as evenly as possible. You can see that they're a bit twisted because what it's doing is it's trying to draw, let me turn off the template flag on this guy here so it's not getting in the way. It's trying to compute the orientation on each one of these curves, and that the orientation of the curve is going to define how these things are actually facing. You can see that reorient curve is enabled by default. If I don't like the orientation here, I can just go in and go to the Orient Curve tab and then just apply a twist. And if I delete the twist ramp and I can apply the twist globally. So if I do, it's going to be like roughly negative 90 degrees. Now these guys are all facing directly down the funnel. The other thing that you could do if you don't like the orientation as it is you could just add a transform modifier after the fact and do rotations here. Let's template this. If I don't like where they're facing, like maybe I want them to go backwards for whatever weird reason, I can just do a rotation here to make up for it. Just 1 second. So another interesting thing that we can do with this, and let's just delete this and go back here. If I go to the Animate tab, this is where you actually control motion for this thing. So there's a number of different controls here. There's a lot of different ways that you can drive this animation, but at the simplest method, all you're doing is just adding to the current goal position. So if I drag the slider along, you can see that what they're doing is just moving from A to B and then wrapping around to the start. And this is because the wrapping behavior here is on by default. If I turn this off and then move the goal, you'll see that they'll reach the end of the spline and then just stick there. The goal type, goal U, basically just means that you're defining a goal for each one of these things and just sliding it across. And if it reaches the end, if wrap's enabled, it'll just go back to the beginning of the curve. But there's a number of different ways that you could potentially interact with this. The arc length mode, I'll show you in a bit, but it means that you can go by length instead of parametric 0 to 1 when you're trying to figure out where each of these things goes. You also have the ability to randomize things slightly. So if you want to just like sort of shift the initial goals around a bit, you can do that, and then they'll still move at the same pace when you move the goal. Another interesting thing that you can do with this that I want to show real quick is, and let me enable the spreadsheet here. I have a workspace that has a spreadsheet on by default, is right now for each of these things, as we move them, we don't necessarily know where they are in along the curve. But if we hit keep goal attributes, what this is going to do is you're given these extra attributes that say that are sort of going to output what is the current goal for each one of these things. So parametrically, where is it on each of these splines? And you have the curve number, which is just which primitive am I attached to. So you can see that curve num is just saying like which curve number am I attached to for each of these things, and the goal is that parametric U for each one of these things. So let's say that I want these things to all animate down the spline. So real quick, I'm going to go to the Animate tab, and let's say, just use a quick expression, time times 0.2. So now if I scrub, they're just going to be moving constantly. I can take these attributes and I can use them to drive other things. So maybe a transform modifier. Sorry. I can use that goal attribute as a fall off. And then maybe I want to scale things down. So now as these pig heads, and let me just scale them up initially so that I don't lose them. But now as they go towards the end of the curve, they're going to shrink down. So having those attributes available to you means that you have like a few more ways that you can influence the sim, because otherwise you would have to sort of manually figure out, okay, well, what is the goal for each of these things? Where do I put it? So you have a lot of options here to be able to kind of take the animation that you've built and use that to drive other effects down the chain. There's a couple of other things here that I can bring up. I don't want to go into too much detail on them, but you have things like obviously the twist thing I already showed you that can be driven by this ramp. So this is like on the 0 end, the beginning of the curve. This is the end. You could define the twists so that they sort of spin as they go down this thing. And obviously, if you're just trying to set like an even twist around the whole thing, you can just adjust the ramp to do it. You have acceleration options, which is basically just saying maybe you want them to move faster at one end of the chain than the other. Right now, by default, the acceleration ramp is linear, which just means it's always going to be moving at the same pace as 0 to 1. But if you wanted to bias this so that they move, you know, you have like an ease out towards the bottom, you can use this acceleration curve to maybe I want like an ease at both ends. And now you can see that they start slow or even I drew that a little too low. There we go. And now they'll accelerate towards the middle and then ease in, ease out. So you have a lot of different options for how you want the motion to work. Also, if you're a VEX guy, you have expressions. And if you turn this on, these are sort of hints as far as all of the different things that you can modify. So if you want to be very specific about the goal for each one of these, you can set it here. And that also includes things like how much random movement do you want, the offset amount, so like the orient offset or the linear offset for each piece. All of that stuff is controllable here in VEX expressions, and you can use any VEX function to output to these variables. Does anybody have any questions about this before I go to the next demo? Okay, I just want to do one more really quick one here, just to show what I mean by the arc length thing, because there's going to be situations where you might have multiple primitives of very different lengths, and you don't want, but you want everything to move at the same speed. So let me explain how that works. I'm just going to make a line here. We're going to have it move along the z-axis. Turn off templating so we're not getting confused. So I've got this little line here, and I'm going to just use the copy and transform stop and translate these guys, let's say, by 1 unit, but we're going to scale up. We're going to double in z with each copy. And I'll make 5 of these. So I have 5 splines of very different lengths. And now I'm going to drop down the usual pig head. Let's put down, I like match size because it makes it'll center the pivot and make the thing unit scale every single time. It's a really handy node to use before going into the instancer. And then I'm going to make exactly 5 pig heads, ones for each of these curves that I've drawn. Let's just template this while I have it on. And one easy way to do that is if I change my distribution mode to linear, I can just say I want 5 points. And so now I have 5 pig heads. And now let's go over to move along spline. And as far as my attachment mode, I'm gonna, I want one of these things to be assigned to each primitive. And if I go to my attach settings, one of the attach methods I can use is attribute. Now, right now, it's basing this on, I'm sorry, this is not the right one. This is still fine. What I want is the curve select mode to be using a primitive number, but I want a specific primitive number. I can just use the ID attribute and it's already ready for me to go, right? Because the ID of these is 0 through 4, and I've got exactly 5 prims that are numbered 0 through 4. So now I'm going to get one of these on each one. And then for the attach method, I can change this to, let's say, attribute. And this can be goal U, that's fine. It really doesn't matter because I don't have that. So this way everything starts at 0 because the goal U attribute doesn't exist, and that's fine. And then the next thing that I want to do is go over to the Animate tab. And instead of the goal type being goal U, I'm going to switch this to arc length. And so what this means is that when I move across the goal, rather than it being parametric, it's going to use the arc length of the curve. Sort of the goal that I'm picking here is actually units. So this first guy is exactly, the arc length is exactly 1 unit long. But for these others, it's double that for each one. So now I can actually move the goal beyond 1. And you can see that as I move this, the other guys are going to wrap around, but they're all moving at exactly the same speed. So if you have a lot of splines of very different lengths, but you want things to still move evenly, you can use arc length mode to control that, and then just, put an expression on goal the same as you always would. And it's just not going to wrap for each primitive until it reaches the end of that length. Let's speed this up a bit so that we can see it a little bit clearer, but you can see that they're all moving at the same pace, even though they're wrapping at different times. Okay. Does anyone have any questions about this operator that they want to ask before we go to the next section? Okay. I'm just going to quickly move on to another similar operator. This one's not used as often because it's a little bit more complicated out of necessity, but there's another one that works with meshes called move along mesh. And it works under similar principles in terms of like you first define an attachment point, and then you define motion. But because meshes are much more complicated, the rules for how you orient things and how you decide how they move are a little bit different. So what I'm going to do is just make the usual pig head here, and this is what I'm going to move around. But first, I'm going to make a template mesh that I want these things to move across. So I'm just going to use let's say the template head. This is a good, easy one. Focus on it here. And then to make this easier, I want to sort of simplify this model a little bit. And it's got this bag on the inside, and I want things crawling around inside this guy's mouth. So I'm just going to blast the mouth bag group, which is built in, just to get rid of that. So now I don't have things crawling around inside there and messing up. And the next thing that I'm going to do is, and you might remember this from the previous tutorial, but I'm going to use Orient Mesh. What this is for in terms of how move along mesh works is instances, and this gets a little bit tricky and it's easier to visualize it. Let me turn on normal display. Oh, that's going to be a little bit crowded. But normals are facing directly outwards. And so when you're instancing things on this, when you think of the normal direction of the mesh, what you want that to align to is, generally speaking, the up vector, because you want your objects to be pointing sort of outwards from the mesh and then moving forward along their normal axis, or like their positive z axis, right? So the way that this thing works when you're orienting the meshes to be used for MOPs move along mesh is you want to use the up vector of the template mesh as your forward direction. And that's why you have visualize up vector on this operator, is so that you can kind of see like, this is roughly what direction that instances are going to go if you use move along mesh. This might be easier if I just scale this guy up a bit so I can see this a little bit more clearly. And so obviously these vectors are a little bit weird. And if you remember from before, when you're automatically computing an up vector on meshes, Houdini is going to guess what you might want the up vector to be by figuring out the difference between the normal and positive z, and then applying that same transformation to positive y to figure out your final up vector. It usually doesn't work the way that you want it to. So what I'm going to do is turn off auto up, and now I have an up vector that is uniform across this entire thing. But you have this option here called cross up vector, and I'll explain a little bit more about this in the math section. But you can see that now now the up vector is sort of flat and attached to the mesh and kind of wraps around it a little bit. The cross product is something that I'll go over this in the next lesson, but it's transforming that up vector against the normals in a way that's going to make it sort of stay stuck to the mesh and wrap around it. And there's a few other options here that I could add if I wanted to in order to make the movement a little bit more interesting. For example, I can add some curl noise so that we get more interesting motion, and you can see these things all kind of bending. Maybe I want a little bit less noise so that it's not overwhelming. You can turn up the frequency so I get a bit more wiggles, but maybe not that much. Turn the amplitude down, and that's similar with blend with original, but you have a lot of different options here for like how you would want to mix something like that in. But again, the goal, what I'm doing is trying to get these vectors to sort of point in the direction that I want things to move. And then finally, I'm just going to call this template because what I'm going to do is instance these objects directly to these points. So let's drop down a MOPs instancer. And I'm going to set the distribution mode to mesh and then just drag the template in as the template object. And let's scatter, we probably don't need this many. Let's start with 50, just so we're not completely overwhelming ourselves. So down here in the scatter settings, I'm just going to set the count to 50. And then I'm probably going to need to make these guys much smaller. So I'll go up to the instancing settings, go to global transform, and then just drag this way down. So now I can see this a little bit more clearly. And I'm going to template this so I can see what's going on here. So I've instanced these guys directly onto this mesh, and you can see that they're oriented a little strangely out of necessity because of how MOPs move along mesh works. But let's add that next. So just like move along spline, your instances are going to go into the first input, and the thing that you want to move along goes onto the second. And just like before, we have an attach setting up front. And this is sort of our first stage, is determining how do we want these things to attach to the mesh. Because we already instanced directly to it, in this case, we don't really need to do anything complicated. We can just say nearest surface, but we could also scatter, and that will sort of run another scatter operation to just randomly decide how you want these things to be distributed on the mesh. Or we can use attributes, in which case you have to provide a primitive on each one that you want to attach to, and parametric UV coordinates on the mesh. If you're not used to working this way, these are the same attributes that you would get from a scatter SOP if you choose to create them. It's also how the VEX functions, XYZ dist and primuv work together. So it can get kind of technical to talk about, but basically every single face here, every primitive face has a number, and that's your source prim. And then each one of those faces, if you were to sort of look at it as a flat grid, has its own parametric UV, where the bottom corner is 0, 0, and the top left, the opposite corner is 1, 1. This can be tricky to generate by yourself. So normally you would use another function to get that for you. For example, I'll just show you really quick on the scatter SOP. If I were to scatter points on this head and enable output attributes source prim and source prim UV, you can see that for each one of these points that I've scattered, I'm getting the primitive number that it's scattered on, and then UV coordinates. The Z attribute is meaningless because we're talking about faces in two-dimensional parametric space. But these are basically the UV coordinates. So where am I attached to each one of these? And these attributes are good to know about because attribute interpolate works with these. The scatter SOP works with these. Anytime you want things to sort of stick in position, the things that the instancer does for you automatically, this is what it's doing under the hood to make that happen. And you can see that it has similar maintain offset, maintain orient offset sliders here. So if I turn orient offset off, what it's going to do is align all of these things directly to the up vector that they're templated to, which I don't want to do in this case. And you also have the linear offset, which here, I need to turn this off on attributes, because what it's doing now is because I have this set to attributes and all of these things have a source prim and source prim UV of 0. If I turn off maintain offset, you can see that these guys are all just going to the 0, 0 parametric coordinate on primitive 0, which is not what we want. We want this to just go to the nearest surface. And now you can see that these things don't really mean anything. The next thing that I'm going to do is go to the Animate tab. So by necessity, this node can't really work as a procedural operation. Moving along meshes is complicated, and every time step, every frame of the simulation, the objects need to be reprojected back onto the mesh or near the mesh based on the offset value you're working with. So it has to be a simulation. By default, all it's going to do is just stick to this thing. But if you enable simulation, now this is where you can actually get things moving around. And I accidentally started at the end of my timeline, so let's rewind. And this is where you sort of have to start worrying about directionality and where these things are moving. The forward vector by default is going to be the up vector, and that's intended to work with MOPs Orient Mesh. Remember that you have this up vector pointing in this direction, kind of sweeping across the mesh here. And so that's the vector attribute, or the relative vector direction that you want to move along for each of these things relative to that mesh. If you're using an Orient Mesh, you don't have to think about this too hard. You generally just want these things to move along this direction. You also have speed and random speed controls. Instead of animating an attribute procedurally like you would with the default method of move along spline, you have to define this as sort of the distance that you want each of these to move per time step. You can see if I just play forward that these guys are following those yellow vectors that we had on the original mesh, and then kind of sliding and orienting themselves to the mesh as they move. You have random speed as well. So if you want some things to move randomly more than others, you can go back and you can see that now we have some that are moving a lot quicker. You also have expressions for this. So if you have this enabled, you can define speed or the axis per primitive. And falloffs also can be used. If you have falloff enabled, then this is going to change the speed. By default, it's going to change the transform, essentially the speed for each of these things per primitive. The other thing to look at is blend in orient. Because these things are in a simulation, what they're you don't want them to necessarily snap to the orientation of the template mesh on every single frame. You want, most of the time, you want smooth motion. If I set blend in orient to 1, this means that on every time step, these things are going to exactly snap to the orientation of the mesh relative to their own local orientation. So if I move the timeline now, you're going to see that as these guys move along, they're going to, especially on this guy up here towards the top, you're going to see that he very quickly, or like these guys on the ear might be a better example, you're going to see that they're very quickly going to snap orientations as they move along this thing. Turning this down means that only 10% of that new orientation is going to be mixed in on every single time step. So that means that as he moves, they're still going to rotate, but they're going to jitter a lot less, which is why the default for this is pretty low. But you can have this set even per primitive that equates to turn rate in VEX expressions. So you can get as weird with this as you want to. The relaxant settings are, these can be weird, but basically the way that things move along, because polygon meshes are imperfect, there's going to be situations where these things might gang up on each other and start colliding. And so the relaxed settings are basically a way for you to enforce a separation between these points during the simulation. You need to be really careful with these settings because if they're set too high like they are now, they can sort of interfere with each other. So usually your point radius scale needs to be pretty small. And now they're going to try to separate from each other and prevent themselves from bunching up in one space, which on a lot of meshes, if you're not careful with your up vector, will happen. Just because your polygon meshes, you're going to have points of inflection, you're going to have concave surfaces where things are going to dip inwards a bit. And so the best way to solve this, in my opinion, is not to use relax, but to be careful about grooming your up vectors so that they're pointing in ways that are not going to cause this problem. But sometimes that's admittedly hard to do. Another thing that you can do in order to prevent sort of jittery behavior on this is on Orient Mesh. If I go back to visualizing this so I can see my vectors here, you can also blur the up vectors to sort of soften the difference between these things, especially if you have a mesh that has a lot of tight folds and corners like the nostrils. You can use the blur options here to basically soften out the differences between these orientations. Then it'll help make the motion a little bit gentler. Does anybody have any questions about this node specifically before I move on? Yeah, anything that you want to do to tweak the up vector, if you want to just copy it straight from something else, that's totally possible. You could set the up vector to be completely uniform. It's what you want. The only catch is that, like, for example, if I turn off all of these options and I just have a uniform up vector for this whole thing, the catch is that anywhere where you're going to have, in fluid simulation terms, it would be divergence, where you have velocities that are moving apart or together, you're going to end up with clumping. And so you can see that here, where all of these guys are just going to get stuck moving straight upwards. And this guy even is getting stuck. He isn't able to get past this, this point here because of the top of the ear is like a point of inflection. Like he doesn't know where to go because he's sort of stuck getting reprojected on the surface individually. So that's where things can get a little bit weird if your vectors are not designed in such a way that they're going to sort of cleanly wrap around the surface. Admittedly, this is a node that is not as easy to use as it should be, and it's part of it is just because parameterizing a polygon mesh like this is not easy to do. On NURB surfaces, this is automatic. And if you remember the old creep sop in Houdini, which I think is still around, the creep sop is meant to take a NURB surface, like a sheet or a patch or something like that. And with that, it's very easy because you can take any NURB surface and parameterize it. You can lay it out in 0 to 1 very easily. With polygon meshes, every single primitive has its own parametric coordinates. And so there's a lot of guesswork involved in trying to figure out where to project to next. What you could probably do, and you'd have to be careful about it. I mean, one option is to just blast out the faces that you don't want it to go to, but another thing that you could do is actually use the comb sop. So if I grab this and actually set my, if I override normal and set this to comb up instead, I can actually go in here, and if I enter the tool state, I can brush the up vector to just sort of paint where I want these things to go on this part. Just this tool could be a little bit hard to see when I'm doing this, but you can see I'm kind of just like parting this area a bit using the brush. And this way instances are going to try to avoid that area when I pipe it into here. The downside of the comb sop is that it's not really procedural. It's a destructive edit. So you have to be careful about that. Okay. The next thing I want to go to really quickly is how some of the Vexpressions in these modifiers work, because this is something that most MOPs operators, modifiers especially, support, but it's good to know kind of how to work with it. So I'm going to make a new container here, and we'll call this Expressions. And let's just make the usual box. We'll give it vertex normals and then drop it into an instancer. And let's set this to be fixed number. I'm going to make this a 10 by 10 grid and just increase the distance a bit. And then frame this. And so now I have this like nice little packed grid here. And I'm going to drop down a transform modifier. So with the transform modifier, let's, I can set translate to 3, whatever. And now all of these things go up at exactly the same rate. But you can dial this in however you want for most nodes. You're not required to only use the Falloff system to modulate how these things might work. If you're a more technical user, you can use little VEX snippets to influence this. For example, if I hit use Vexpression, and most nodes will have a checkbox here somewhere with a hidden Vexpression box that contains sort of hints about what things you can modify, what the different channel variable names are that you can change. So if I want each of these things to translate differently, by default, translate is whatever the channel value is. So it's going to be a vector 030, and it's written here as an example, translate equals 000. If I were to just copy this without the comment flag and paste it at the bottom here, now everything is translated to 0. If I set this to 1, it's going to be evenly distributed across the board. So these things essentially mean the same thing. This is just an override on these settings. But I can set this in a lot of different ways. For example, if I want this translate vector to be, you know, a trigonometric function, right? A sine wave. I could do something like translate y. I'm going to multiply it because it is still reading this channel value. So currently it's 0, 3, 0. I'm just going to multiply the y component, so the second component, 3, against a sine function. So let's say I'll do the time times 2 to speed it up a bit. And then I want it, if I just do it like this, you can see that it's just going to bounce up and down. But I could make this a unique sine function for every one of these things by adding some random amount to the value I'm computing, maybe the ID attribute. And now I get the same overall motion. So it's going to be translating overall by amount of plus or minus 3, because a sine wave is going to return a value by default between -1 and 1. But now it's going to just have each of these things sort of move randomly between -3 and 3, offset over time. So this is a relatively simple expression. You can get a lot more complicated than this if you want to. You can write as much vex as you want. But the point is that these hints are essentially pointing at things that are defined in this interface, and you can write snippets to modify or override any of them any way you like. For example, local here is the same as this local space checkbox. And so you can have some move in world space and some move in local space. Most of these things can be modified that way. Let me just do another quick example here. I'm going to take like a box again. And in fact, let's just do the same exact thing. I'm just going to copy paste these first 2 nodes. And now let's do this. Let's keyframe a couple of things. I know you Houdini guys hate doing that, but sometimes keyframes are nice to have. I'm going to drop down the transform modifier. And what I want to do is make like a little pulse motion. I'm going to have these things sort of move down like they're attached to a spring and then pop back up. So I'm just going to key translate y at the beginning here. And then let's say for 16, 18 frames or so, I'm going to have it move down about 1 unit. And then for the next frames up until 1 second, so frame 24, I'm just going to pop it back up to 0. So now all these guys are moving exactly the same way. It goes down slowly and then pops back up. Now what I can do is put down a MOP spring modifier to apply spring forces to this, which I believe I demoed last time. And really quick before I get, I have some settings that I know are going to work for this. I'm just going to set the mass to 2 so they've got a little bit more weight, and then leave these other things alone by default. And then before I go further with this, what I want to do is apply a fall off so that each one of these things looks a little bit different. And it doesn't have to be complicated. I'm just going to use a shape fall off. And what I'm going to do is use this fall off to modify those different physical characteristics of the spring modifier. And that'll make sense in a second. I'm going to preview fall off. The auto fit button here on shape fall offs is going to automatically fit the shape function to the bounding box of the objects that you have contained. So if I just hit this real quick, it's going to roughly fit the exact bounds of this. So I don't have to really dial this in. And now I'm going to go to the spring modifier and start messing around with expressions. So quick example, if I turn this on, you can set the same physical characteristics, the mass, the dampening, or the spring constant using these values. And if you're ever confused about the labels here, a lot of the time the parameter names, like if I hover over this, for example, this is D, that's your damping. If I hover over this, the spring constant is K, so that's what this is pointing to. With VEX, it's a lot easier to keep your variable names short, which is why they look like this. And K comes from Hooke's law. It's like a physical function. So I'm using conventions there. But if you're ever not sure what these things are supposed to be connected to, hover over the parameter names, and usually that's where you'll find the hint. But what I can do now is I can modify any of these values. For example, mass, I can multiply against MOPs falloff because that attribute exists on this shape. I'm going to disable this first so that you can see what this looks like. All right, I'm sorry, not this. I'll disable the expression here. So if I run the spring modifier on this, you can see that every one of these things bounces evenly. I'll just play back one more time. It goes down and then pops back up, and then you get this nice little spring motion at the end. If I enable this expression, now I'm using this falloff to modulate the mass directly, which is not something you would really easily be able to do without a expression. And now when I pull this down, you can see that, oh, that one just flew off into space, but they're all going to be sort of understanding the mass differently. So real quick, the reason that's happening is because these guys on this end, their falloff value is 0. And so I effectively made a bunch of boxes with 0 mass, which Hooke's law does not like, because now these boxes are photons. They have no mass at all, and they're going to fly off into infinity. So what I can do to fix that is go into the shape falloff, remap. I'm going to enable fit, and then just change my output minimum to be something very small. And now I never have anything that's completely massless. And so if I rerun the simulation, everything's fine. So pretty much every modifier in MOPs has the ability to use expressions to modulate things. And when you're in any situation where you want to change something that's not easily affected by a falloff, this is often one of the best ways to do it. And your expressions don't have to be complicated. A lot of the time, it's just as simple as going in and multiplying some parameter against a falloff or some other attribute you have. It can pretty much be any point attribute, because everything in MOPs, is, with few exceptions, is running on points. Any other questions before I keep going? We got a lot more to cover. One other advanced node that I want to show you that a lot of people don't really know about is MOPs neighbors. And it's kind of a weird one. It doesn't get that much use, and I think it's just because the utility of it is very specific. But essentially, if you remember the plexus effect, which I think was something that Cinema 4D had, am I right? It's about drawing connections between things and doing it in a way that is configurable in a few different ways. So just to show you what this looks like, in an easy mode here, I'm gonna just drop down a sphere and an instancer, and let's set this to be a fixed number. I'm just gonna make a 10 by 10 grid of these spheres. And then let me just grab the global transform and scale them down until we have separation here. So I've just got this simple grid of spheres. And I'm gonna put down a noise modifier, I guess. Yeah, let's just add some noise. And I'm gonna have this affect, obviously just the position. And that might be a little intense, but no, whatever, we can leave it like this. And I'm just gonna turn on time varying. And so now I have all these guys wiggling around. Now I'm going to drop down MOPs neighbors, which is listed as a tool node because it's not quite a generator and it's not quite a modifier. It's its own weird thing. That'll make more sense once I turn it on here. So when you first drop down neighbors, there's two modes. There's find neighbors and connect to them. What MOPs neighbors is actually doing under the hood is it's finding nearby points and establishing a relationship with them. And what that looks like is this attribute here in the spreadsheet, which is just an array. And this is an array per point of all of the things that this point is associated with. At its simplest, it's basically going to work like connect adjacent pieces or connect adjacent points does, which are built-in nodes that you might be familiar with if you're trying to do constraints to draw polylines between things. And these two outputs, one of them is just is a pass-through. These are your same packed primitives coming out the other side. So if I drop down a null here, it's exactly the same as what I was just displaying. But on the right side, you have the actual primitives here. And real quick, I'm just going to apply some color to these so that we can see them separately a little bit better. Let's make them red and then merge them back into the original stream. And if I animate this, you can see that every frame, the neighbors are changing. And so these connections are constantly sort of disconnecting and reconnecting, redrawing themselves over time. I'm just going to copy this setup real quick here and paste it and show you a couple of different ways that you can leverage this. So again, I have find neighbors set, and maybe on this version, and maybe I'm gonna, the search radius of 0.25 is fine. What I can do now is, again, I have the pass through here and the neighbors here. And again, I can merge them together so that you can kind of see what we're looking at here. It's just going to be, oh, what happened there? I think my viewport's stuck. Sorry, 1 second. Interesting. So a channel actually broke in a way that is kind of convenient, but I'm not sure why it pasted this way. Let me just grab this neighbors again. Okay. So what I wanted to show you is that, again, if I animate this, you can see that this neighbors network is being redrawn every single frame, and the neighbors array is also being recomputed every single frame. But that's dependent on this thing called the reference frame. If I want these connections to be established only once and then be consistent from frame to frame, I can just delete this expression, which by default is just $F, it's the current time. But I can set this to be whatever frame I want. And so now if I scrub this, you can see that these connections don't move, and the attributes themselves also aren't changing over time. So it's only storing the neighbors at a given point in time. MOPs neighbors has a second mode that you can activate after the fact here. That's called connect to neighbors. And so what this will do is read that array and redraw those connections after the fact, regardless of where they are in time. So if I put down a null here, and these are the new connections, and then we'll just template this. You can see that now, instead of those connections being redrawn and recomputed every frame where you have lines disappearing and appearing, what it's going to do is stretch those lines so that they remain connected together. And all this is just using the connect to neighbors mode. It's reading this array and then drawing those connections between those points consistently on every frame. There's one more way that we can use this that's a little interesting. Just 1 second. I'm going to copy roughly the same setup here. Actually, let's do it slightly differently. I'm going to start with the same sphere grid. But what I'm going to do is group these, turn off template, and I'm going to call this group ends. And what I can do with MOPs neighbors is be specific about who gets to connect to who using groups, which can create slightly different effects with this if you're trying to draw specific connections between things. And then let's create just a plain box. And this is going to be sort of our start object, our master object that's actually drawing these connections. And I'm going to just turn it into a packed primitive real quick. I can just use mops convert for that. And let's move this box off center of the main grid here a bit. So let's move them up here and then maybe out this way a little bit. And then turn the scale down considerably. Yeah, that's fine. And now what I'm going to do is put down a transform, just a regular transform on this, because I want it to just move around from the origin and just rotate it. Let's do frame times 5. Now what I have is just this guy spinning around over this group here. And then I'm going to group this and call this guy start. And I think, I don't think I want these to be primitive groups. I want these to be point groups. MOPs deals with points. Let's just switch that over for both of these. Okay. Now I'm going to merge these streams together. And one thing that you might notice is you're going to see this little exclamation point because we have an attribute mismatch. But the other thing that I want to bring up is that, and this is something I'll go over later in the lesson, I have multiple points with the same ID now because I'm merging these two streams together. So you can see that this guy starts at ID 0, and so does this one. So one thing to keep in mind is you can adjust this very easily by just going to the sorting tab of the instancer. And I just want this guy to start at ID 1 instead. And now I don't have duplicate ID attributes. This guy is starting at 1, this guy is starting at 0. When I merge them together, I have that first guy at 0, and now I have no duplicate ID attributes. This is important, and I'll go over this again later. But you want to make sure that you don't have two IDs that are the same, or else MOPS is going to freak out about it. So now I can drop down MOPS neighbors. And I can put this in find neighbors tab, but instead of just find nearest, I can do start and end groups. And so when I do this, and then let's just highlight the primitives that are created here, I might need to crank my search radius a bit. Where is he? Oh. Oh, it's because I named it ends instead of end like an idiot. Okay, so if I change this to ends and then view this, now you can see I'm getting these connections. And so what it's doing is I'm getting these connections to each of these points within this search radius per frame. And again, this is something that you could, let me just colorize this so it's a little bit easier for you to see. But this is something where you could, again, use those time attributes if you wanted to be specific about what frame determines the frame that, what frame determines which connections are going to be valid, and then draw those, and they could stretch or they can generate each frame procedurally like this. Let me just merge this together. So now you can see that it's drawing connections per frame from object A to object B, and you can have as many starts and ends as you want for this thing to be able to draw connections between. So the idea is to be able to get your classic kind of plexus effects where you're just randomly or not so randomly connecting things together that are nearby, but with like a little bit more control than you get from just connect adjacent pieces alone. So I am going to go to the next section here real quick. Just give me 1 second to open the file. And what we're going to talk about now is things that modify time. So there are a few different nodes that can change timing on things, and this can make it a lot easier to create really complex behavior from very cheap animation. So as an example, really quickly, I'm going to make a new container. We'll call this delay. And we'll start with a really simple one. I'm going to make a pig head, match size it. Its centroid is correct. That looks fine. Let's scale it down. And then we'll pipe this into an instancer again. And we'll just use the linear distribution mode so that we can see this a little bit more clearly. And I'll have these guys moving along. Let's do this along X. Whatever, I guess it really doesn't matter that much what direction they're in. And let's make the length 10. Got these guys aligned here, and then orientation, I'll just turn off a line. So I have them all facing sort of in positive Z along this line. What I'm going to do is just scale these guys up over time. So I'm going to use a MOPs transform. And at frame 1, let's just scale them all the way down. And then we'll have them scale up over 1 second. So really simple, boring animation. And obviously this is this is not normally what you would want to do. Like, this is very boring. There's not a whole lot of organic feeling behind it, but you also wouldn't necessarily have to, especially if you want more complex behavior, you don't necessarily want to try to figure out exactly how to align a fall off to get this to work. And even with a fall off, you can have things sort of slowly blend from one transform to the other, but you're not going to be able to get more complex behavior than that with a single fall off, especially when you're chaining together multiple animations and you want them to all sort of feel like they're time offset for each other. And so that's where MOPs delay comes in. MOPs delay can be applied to basically any point attribute or to any component of a transform. It doesn't work for complex deformations. So if you have like characters running, it's going to have a harder time delaying those. And with some caveats, you can do it, but I'll get into that a little bit later. But what delay is going to do is it's going to read the fall off value of each of these and then delay the transforms of each of these objects according to your delay amount in seconds or frames, depending on how you like to work, times that fall off value. So you can see here, if I go back to the frame 1, my delay amount is 0.5, which means half a second, 12 frames. And it's applied evenly to everything because all of these objects have a fall off value of 1. So if I go to frame 12, you can see that I'm still at scale 0, but by 13, this is where you start seeing that there's actually geometry. And so they're going to just do that whole animation, but half a second too late. The power of this is obviously when you start introducing fall offs. So I'm just going to put down a really simple shape fall off. And let's preview this really quick. I'll do the auto fit. So now it's just 1 to 0 across the board here. And then let's rewind, turn off preview fall off, and go back to MOPs delay. And now when I play, you can see that they fade on at different times. So this will apply to all upstream transformations. So you can have as many different motions as you want going into this. And MOPs delay is just going to time offset all of that according to the fall off. So let's go to a slightly more involved example. Just give me 1 second to set this up. Let's make this again. Let's just do a really simple box. I just like to, when instancing things, I sort of like to use match size just as a matter of course, because it sort of unifies how things are built. It's just a safe way to make sure that you know exactly what you're getting when you're going into the instancer or the copy to point stop. And scatter align almost, if you're using scatter align or any of Houdini's native scattering features, it almost insists that you're using match size on everything. It wants everything to be unit scale. So it's a good thing to get used to. I'm going to change the distribution so that I have, let's say, a 10 by 10 size with a step of 1 for each of these. And then I might need to just scale these guys slightly differently. It's, sorry, just 1 second. Well, this is fine. Yeah, so these guys are all basically evenly, you can't see any seams because we don't have wireframes enabled and all these are packed, but whatever, we'll start with this. So what I'm gonna do first is make a really simple animation of these guys sort of appearing. So again, I apologize, but we're gonna have to set some keyframes. At frame 1, I'm just going to have these guys scale all the way down like the last one. And then over 1 second, let's scale these guys up and maybe have them, let's have them rotate too. So I'm set a keyframe here. And then at 1 second in, I'm going to have these guys rotate 180 degrees. So again, pretty boring animation. The next thing that I want to do is maybe have them all raise up a little bit. So I'm just going to put in another transform modifier after the fact. The reason I'm doing this is because I don't want the rotations that I'm doing in this first one to get in the way. And I also want to show you that you can chain multiple transforms, nodes, whatever you want into this, and delay is going to work with all of them. So you don't have to worry about delaying things individually. Any transforms that you do up the chain are going to be delayed by MOPs delay. So let's say maybe just a second after this, or not even a second, like maybe a few frames after, I'm going to keyframe translate. And then 2 seconds in, let's just move them up by 1. So now I have this sort of spin and then everything moves up. What I can do now is I'm going to create a couple of different fall offs in order to sort of, well, it'll make sense in a second. I'm going to start with a plain fall off. And what I want to do is have this plain fall off animate from 0 to 1, kind of around the same time as this second move. So let's start it here and then end it here. It's fine. If I preview this, you can kind of see what I'm doing. And then I'm going to drop down a color modifier. Because again, color is a point attribute, and so MOPs delay can delay this as well. So what I'm going to do is these things start like this, and then they're going to turn red as they reach the end of their movement. And then let's do another shape fall off. And let's make this spherical. I'm probably gonna have to make it significantly larger. Let's actually I can just do this. Let's reset this to the defaults. Set 0.25 and 1. And then I'm gonna just bump this up a bit so that it's in the middle here and just use the uniform scale so that I don't have to worry about my inner and outer radiuses changing too much. So I think about 5 should do it. Yeah, that's roughly it. And if I preview this fall off, you can see that I'm getting just this sort of radial drop off here. And now MOPs delay. Sorry for the long wait here, but the idea is to show you that any attribute can be delayed. So anything that is going to be written out as a point attribute on the spreadsheet can be delayed up the chain. So it's not just limited to transforms, it's any point attribute. So if I run the sim now, you can see that the center points are going to come in later than the other ones. And the color change also follows the same rules. It will work for almost any point attribute, except for things that can't be interpolated like strings. Integer attributes will have a little bit of trouble, but almost anything else will blend evenly through the delay. And one other trick that I want to show you with this before I keep going is that this isn't just for packed primitives. You can use this on any points. So as a quick example, I'm going to grab one of the MOCAP bipeds, like just the built-in guys. Let's grab number 2. Turn this off for a second so I can see him. And MOCAP biped 2 comes with like a handful of different motions. And I just want to pick something that has a lot of movement in it. So I'm just going to grab jogging here. You can see it's just this dude jogging. Great. Turn him off, go back into my network. And I'm going to merge him into this scene just to show you what I mean. So go to MOCAP biped, and inside MOCAP biped, there is a geo network. And I can just grab this whole thing. And now I have this dude as SOP geometry in world space here. In order to get MOPs to work with things, as always, you need an ID attribute. And there's a number of different ways to generate that. I don't want to run MOPs convert on this guy because I don't want him to be a packed primitive. I want him to stay as a mesh. If you want to generate an ID attribute, there's, you can do it in VEX. It's not hard, but there is actually a SOP built in called enumerate that does essentially the same thing. So if I change the group type to points and then set the attribute to ID, now I have an ID that's just equal to the point number. So it's just a quick shortcut to be able to do this. You could also, if you wanted to, I do this a lot, is just use a point wrangle and then just say I at ID, because it's an integer attribute, equals point number. And it means exactly the same thing. But I need this going in because MOPs will not work correctly without an ID attribute. That's pretty important. Now I can create a shape fall off. And let's just make it vertical so that one side is going to be more delayed than the other. It's probably fine. Maybe I can scale this down just a hair so I get more contrast. And now MOPs delay. And I think half a second is probably fine for this. Yeah. But now when I run this, you can see that I'm getting this kind of weird slit scan effect. So this will work on any kind of point geometry. So if you're trying to do some more unusual deformations, or if you're not using packed primitives for whatever, if you're trying to delay some other attribute spreading across a surface in something that is completely unrelated to MOPs, you can do that with polygon geometry or a point cloud or anything else you want. It doesn't care. So this one's pretty powerful. You can do a lot with it, especially if you're kind of thinking outside the box. But for like basic motion graphics stuff, it means that you can get really complicated behavior for cheap. The only downside to using this is that it is a simulation. So you have to be careful about anything with a sim. If you change any of your attributes upstream, all of that time, you want to make sure that you've got this reset simulation button handy so that you can recompute stuff in case an input changes. Just keep that in mind. Spring is the same way. It's a simulation. So if you're not getting the results you expect when you change something, make sure you got the reset your simulation button handy. Okay, I'm going to go into the spring mod now. This one is a little bit trickier to use than delay just because there are a lot more controls or a lot more sort of little finicky things that you have to worry about. Just as a quick example of this, let's do a MOPs explode on a sphere. So each one of these primitives now is its own separate packed primitive. And I'm just going to sweep like a quick and simple animation across, like nothing fancy at all. I just want this thing to like grow into position and maybe rotate a few degrees. So let's start with the transform modifier. And let's say I want these things to all go, I don't know, maybe half a unit inwards. That might be too much. Well, no, that could still work, I guess. But I am going to increase the frequency of this sphere a bit. Let's change this to a polygon instead of a polygon mesh, and then bring this up to 4. So we've got a decent number of points of triangles here that are all the same. And yeah, let's move these guys in by about -0.5 and then scale them down to nothing. And now before this operation, or here, let's set a keyframe so that we're doing this. Sorry, just 1 second. Okay, let's use a Falloff just to blend this out. I'm going to move it over here. I can't preview on this accurately because these are packed fragments, and I'll explain more about that later. But what I'll do is just scale this guy down a bit, move it here, and then I will set a keyframe on translate here. And then just a few frames in, because spring works better when it's more exaggerated anyways when you have things moving very quickly. I'm going to have it animate on, and we'll just do that there. And now when I go to my transform, I have this kind of effect where these things are starting kind of small. Might have to push that a little bit harder. Yeah, there we go. Okay, so I have the fall off sweeping entirely across, and I have this motion happening. This is kind of going opposite of the way that I want. I want these things to be appearing and not disappearing. So I'm just going to remap the shape fall off to invert the output min and max. So now it's a fade on instead of a fade off. And now let's do the spring mod. So what the spring modifier does is it applies Hooke's law, a simple physical function, to the transforms of your primitives. And so anything that you do to position, rotation, or scale is going to be kind of run through this simple bounce function. The spring forces are a bit hard to tune, but the three that you're sort of worried about, the 3 parameters here that actually matter are the mass of each object, the spring constant, and the damping coefficient. And these, I'm sure these words are sort of meaningless, but basically, when you're using Hooke's law, which is like a very simple physical equation for like ideal spring forces, the mass of the object is basically how much does it resist change. The spring constant is a measurement of how stiff the spring is. And so a much higher number is going to be a tight spring that really wants to reach its goal or its rest length quickly, whereas lower numbers are going to be more wobbly. And the damping coefficient is what it sounds like. It's sort of a measurement of energy loss during the simulation. If your damping coefficient is 1, it means there's no energy loss at all. And what that translates to in terms of springs is it means that your object will bounce back and forth forever. The default is 0.9 because it means that you have a little bit of damping, but not too much, which means you'll get a pretty bouncy spring, but it'll eventually reach a resting point. For this one, I know that I want the mass to be about 2 and go middle of the road for the spring constant. So it's a fairly loose spring, and then turn the damping down so that it quickly loses energy. And now when I do this animation, you can see that things fade on like they were before, but you get this kind of wobble after the fact. One thing that I should mention with this, and one of the reasons why these parameters can be hard to tune, is because they're very scale dependent. So depending on how much things are moving, how fast they're moving, how big your scene is, you're going to have to tune these on any given scene to get them right. And so there's no, the default values are good for some things, but it's not something that you're ever going to get right every time the first time. You really are going to have to spend some time tuning it. I just want to do one more example if I have the time. Drop down a box, get some vertex normals on it, and then do a grid, and then a copy to points. Make sure we're instancing. Great, we've got a grid of cubes. I want these things to be moving from the bottom. So real quick, I'm going to do a match size again and just justify the minimum. And I did that on Y. Oh, you know what? This I need to orient this because again, grids that are facing in positive Y. I touched on this in the first lesson. That grid's normals and up vector are facing the same direction. So it's making all of these cubes orient in a strange way. So if I turn off auto up, you can see all these things shift. And this is because now, originally this grid, if I were to look at the normal vectors and the up vectors, they're pointing exactly the same way. But with MOPs Orient Mesh, if I turn on visualize up vector and I turn off, you can see that now up is facing in a weird direction, which is why the boxes that I'm copying to it, when I think I'm matching to Y, they're not. So again, let me put copy to points on here. So just to demonstrate this again, if I set this back to center, what I was trying to do is get it so that they're resting on the ground plane. And so I figured, oh, I'll set justify Y to center or to minimum instead of center, but they're all shifting in the wrong direction. And that's because of the implied up vector when you have up and normal facing the same way. If I turn this off and I explicitly define the up vector, now these guys are actually going to be sitting on the ground plane, which is where I want them. Okay, so now what I'm going to do is really quickly, I'll run a MOPs convert to make sure that these guys have an ID and a name attribute. I'll set this to packed primitives. And now I've got ID and name for each one of these pieces, which is great. And then let's do a transform modifier. And I'm going to have these guys scaled down to like something very small so that they're a pancake now. And that's interesting. Maybe I wanted this to be. Oh, that's right. They're scaling up from the wrong side. Why is that? No, I think that's correct. Oh, you know what? I got to change the pivot location from the centroid to origin. There we go. Another reason to use the instancer. I just wanted to show that you can, if you need to use vanilla Houdini workflows with this, you can. It's important to remember MOPs is not a closed system. You can mix and match as much as you want, but it does mean that you have to worry about all these checkboxes. And now let's do a spread fall off. I'm going to just do a quick sweeping animation from one side to the other. And for my start point group, let's just pick, you know what, this will look better if we're using a longer grid. Let's do a 4x8. And then I'll just turn this box's size down a little bit. Yeah, so let's sort of display the effect a little bit better. So what I'm going to do is sweep a fall off from one side to the other and then do another quick transform. So for spread fall off, let's pick this guy as the start point and turn on preview fall off. And I'm just going to animate this going from, animate the spread from 0 to 1 over, say, just 1 second. Just like that. And I can add noise to this too. Maybe that'll make it more interesting. So now when I sweep it across, you can see I've got like sort of just a noisy running edge. Maybe I can drop the frequency just a little bit. Okay, cool. And what I'm going to do now is have these guys all sort of scale up quite a bit. So another transform modifier. Scale this to like 200. So now as these guys scale up, or as the fall off sweeps across, they'll scale up. And now again, spring mod. And I'm just going to dump in some settings here that I know are probably going to work for this scene scale. And you can see that it's not just position and rotation, scale can also be sprung. You can even affect sequence time. So I'll explain this in the next section when we talk about more timing adjustments, but you can use this and delay to do the same thing to baked sequences that you want to adjust the timing of. This is a good way to get just like a little bit more organic life in anything, just by adjusting these parameters and messing around with fall offs. Like you can do a lot to sort of tweak the timing of the things without having to set extra keyframes. Because now I want to start talking about all this sequence stuff that I'm bringing up. Okay, here we go. Just going to turn this off really quick. So sequences are a really big thing that a lot of Houdini beginners ask about when they want to be able to have, like, you know, your classic flowers blooming simulation where you have all this beautiful animation of a flower opening up, and now you want to copy that to a bunch of different points and have each one be different. But it turns out that that's kind of tricky to do. So MOPs gives you some controls for this that are going to make your life a lot easier, and I'll show you those now. So I'm just going to open up a new geometry container. And actually, first, before I do this, I want to just make a really quick, easy sequence, like a looping animation that we can work with. I'll use biped 1 for this because he just has this built-in walk that's really simple. And I know how many frames long it is, so it's easy to start with. I'm just going to turn him off and then dive inside this network. The one trick with sequences and MOPs when you're adjusting timing of things that are deforming, things that aren't just rigid transformations, is that they have to be baked. You have to cache them to disk first or they won't work. So if you're just, you know, translate, rotate, scaling things, then you can use tricks like MOPs delay or other things like that. But if you need to do something that's deforming and you need to adjust the timing of a deforming animation, it has to be cached to disk. And it can be either cached as an alembic or as a packed disk sequence or as a series of files. And I'll show you what that looks like in a second. I'm going to just go into MOCAP biped 1 here and again, find the geometry network inside and then merge him in. So now I've got this walking sequence here. And I happen to know, I'm going to make a ROP geometry output. And it's fine to just use the default here. I get, you know, it doesn't matter, whatever you want to call it. I'm going to call the name walk so that the sequence at least comes out with that name when it writes. So I'll have, yeah, untitled walk1.bgo. And then I'm going to change the frame range. I happen to know that this loops at about frame 26. So I'm going to write from 1 to 26 and then just save this to disk right now. And if I just set the file stop at the default options, once I get past that frame, if I scrub past, it's going to throw an error because there's no longer anything there. But this is only one way that you can load geometry in. There's also something, if you go to load all geometry, there's something called a packed disk sequence. And this is basically a special kind of packed primitive that Houdini will stream from disk at render time. If I switch to packed disk sequence, you can see that it just turns it into a box. The Houdini, the MOPs instancer, by the way, will load packed sequences. And I think I showed you that in the first lesson, but if I didn't, you can pump files in directly and it will load them as packed disk sequences automatically. If I set this to full geometry instead of bounding box, now I can actually see the sequence. The one downer is that you have to tell Houdini specifically exactly how many files are in the sequence. So I'm going to change this again to 1 to 26 because I know that's how long it is. And now when I scrub, A, it loops, which is great because by default, loading a Houdini file sequence like this, you won't get that. And B, you have other modes, right? You can mirror, you can clamp. So if I hit mirror, he's going to walk forwards and then walk backwards and just sort of bounce back and forth indefinitely. You can also clamp so that he'll do one cycle and then stop, but he won't disappear. He won't throw errors. You can also load alembics. to that walk.abc. And similar, but you don't have the ability to set any of these abilities like wrap modes. The differences between using packed disk sequences and alembics are mostly about preference and pipeline. Packed disk sequences are really efficient to load. Houdini, it sort of treats it as a delayed load. So if you have a really dense scene, they're really efficient. They support motion blur and they support subframe interpolation. So if you're trying to do like a real slow-mo scene and you need to adjust the timing on a packed disk sequence, Houdini, Mantra, and Karma all know to sort of interpolate the between the lines, like on subframes, which can be really handy when you're doing slow-mo or when you're doing really drastic timing adjustments. The downside is that packed disk sequences generally aren't well supported by third-party renderers. So if you're using Mantra or Karma, you're fine. But if you're using something like Redshift or Arnold, different render engines might have different levels of support for Houdini geometry, or for packed sequences specifically. But in general, they're not well supported. And just one other quick thing I want to point out, when I highlight this, you can see that this packed sequence, when I click on this, is a single point. Packed disk sequences are packed primitives. If I middle mouse on this, you can see that it's just reading one packed sequence. And if I go into the spreadsheet here, you can see I've got intrinsics, and a few of them are file names. And this is basically an array of every single file path in that sequence. There's also the index, which if I turn file names off, you can see as a number, and this is actually pointing to which file in the sequence we're loading. And you can, but it's pointing to it in a weird way because it's, at frame 130, it's index 129, but that's sort of applying the cycling behavior after the fact under the hood. So it can get a little confusing, but this is how Houdini understands how to load this geometry, is again, using these sneaky hidden attributes. So alembics are much more widely supported. And again, alembics, when you load them in, aren't necessarily alembics. They're usually being loaded in by default as delayed load primitives, which is something that a lot of render engines understand. And it's also very lightweight. Houdini doesn't need to open these things up and expose them as polygon geometry. It can just stream them in from disk, which makes them very efficient. The downside is that they don't have any of the built-in controls for cycling behavior or any of the stuff or the subframe interpolation that you get from packed disk sequences. Another way that you can load files from disk is by using a point attribute called instance file. It's a string point attribute called s.instance file. I'm just going to make like a point in space here and then drop down a point wrangle. And I apologize for the expression I'm about to put in here because it's really ugly. But this is sort of the third way that you can use to delay and load things. And this is a big ugly expression that's basically loading that same walk cycle that I just dropped in as a BGeo sequence. And if I load instance file in here, you can see that as I scrub the timeline, this expression is evaluating to the full path on disk to those BGeo files. So as I scrub the timeline, you can see that this file number correlates to the file on disk. Instance file is sort of an object level thing. It doesn't really work in SOP networks. So if I go to the object level, you may or may not, you might not see it. Sometimes you'll actually see the instances load in the viewport, but it's not super reliable. Instance file is compatible with most third-party render engines, Redshift included. It's very flexible. You can point to any path on disk you want, but the downside is that this really sucks to write. Like, you don't want to have to build these expressions every single time. It's kind of nightmarish to work with. I'm just going to put a switch down here so we can compare these three things a little easier. The other downside is that if you want to adjust the timing on any of these options, for example, if you want to adjust the timing on this packed sequence, you have this index attribute, but you have to set this. So you would have to use VEX to say set prim intrinsic, and set the index attribute to be the exact frame number per instance that you want to work with. On the Alembic, if I switched here, you have similar intrinsics like ABC frame, which annoyingly enough is not actually a frame. It's actually referring to the time in seconds. So you have to make that calculation under the hood, figure out exactly how many seconds in you want this alembic to play, and the cycling is up to you. You don't have alembics will not automatically cycle. They don't have any built-in modes for this. It's just going to play and then stop. So you would have to do any of the math to make that work. And then obviously this, like you're sort of you just have to write this out manually and hope that you get it right. So here comes MOPs. Set sequence time treats all of these things as exactly the same problem. It doesn't care what you put in. All it wants to know is what frame index you want, and if you want to set a cycling mode or override an existing one. So for example, if I go to this first one, and I have, right now it's matching the frame index to exactly what the current frame is, right? So it's just saying frame. But I could set this to frame plus 20, and now he's going to move and start walking again. So I just time offset him by 20 frames pretty easily. You can also adjust the cycling mode. So even after the fact, although I had already set the cycling mode when I first loaded this packed disk sequence, I can override this and say, well, actually, I want this guy to mirror. And now he's going to walk forwards and then backwards again. Maybe I want him to, I don't want that time offset anymore. So you can set all this up very easily and this is just for a single guy using expression. We also have the ability to use attributes to control this, which I'll go over in a second. And the same thing goes for alembics. So if I switch to this alembic mode, I don't have to worry about the different intrinsics. I don't have to worry about the different timings, and I can override the cycling mode here pretty easily. I do have to set a frame range for this because alembics by default don't determine what the frame range is. And so if you're loading in an alembic and you want to control the timing of it using set sequence time, you're going to want to enable this and tell it what is the frame range that I want to iterate over. But now it's the same thing. He's walking forwards, now he walks backwards. And this is a behavior that you can't get built in with alembics. Or I could just set him to cycle. And now I have a walk cycle being driven by an alembic instead, which is great because now I can control it and still use third-party renderers. And the same thing goes for if I'm using instance file, and this is harder to visualize just because the viewport, oh, now it's showing it, go figure. But now you can see that this is using the instance file point attribute to load these things off of disk, and I'll just expand this so you can see it. Of course, it's not updating in the viewport, it's great. But it would render. I apologize for the weird Houdini viewport issues, but it would render. But you can see that it's going through this list of BGO files, but then once it reaches the endpoint, let's make sure I've got this set correctly. There we go. So now you can see that when I reach frame 26, it pops back to frame 1. So it's going to do all of the complicated, annoying math to cycle all these things or to clamp them or to mirror them, whatever it is that you want based on the frame range you provide, and you don't have to think about it. So this comes especially in handy when you're trying to load something like a Redshift or a Arnold proxy file, because both of those render engines support the ability to use instance file to instance things from disk. And so if you have a really complex set of Redshift proxies sequences that you've animated, you can copy them to these points or use this instance file method with sequence time to have whole crowds of things loading in as Redshift proxies, which are really efficient and you won't run out of VRAM rendering them. So let me just go in a little bit deeper with this sequence stuff just so you can better see how this works. I'm going to start a new geometry container here. And let's load in that same alembic that we made last time. So I'm going to bring in that same walk cycle. And then let's do another grid and an Orient Mesh. I'm just going to do the same thing I did before, where I am explicitly defining an up vector and then copying to points. And one thing that I should note is that I am not turning on pack and instance here, because if I middle mouse on this, these are already packed. They already have packed transforms. I don't want to change that after the fact. So now I have this whole army of dudes strolling, but again, because it's an alembic, they're all doing the same thing, and they're all clamping at the end of the sequence because that's the intended behavior of alembics. So I'm going to put down a shape falloff. And let's just auto fit this to the scene. And then, yeah, okay, preview fall off. We've got like a clean, even fall off value going across the whole thing. And now let's use set sequence time again. So what I can do with this is instead of just using an arbitrary expression, I can use an attribute. And that attribute by default is MOPs falloff because it's kind of expecting you to do this sort of thing. Instead of set, what I can do, because if I set right now, you can see that none of these guys are moving because they're all just reading the MOPs falloff value and setting that as the current frame index. And falloff is just between 0 and 1, so that doesn't help us much. I'm going to go back to the shape falloff. And I know that the sequence is exactly 26 frames long. So if I turn on fit, I can change my output maximum to 25. So now my MOPs falloff value is all these random numbers between 0 and 25 going across this whole geometry stream. And now I'm going to change the mode to add. So what this is going to do now is take that falloff value and add it to the time index of each one of these sequences. Because these are alembics, I have to enable these two overrides. So I'm going to turn on cycling mode and set it to cycle. I'm going to make sure that this thing knows that the frame range is 1 through 26. Once I've done that, now you can see that all of these guys in each row, based on that fall off, are in a different step. And if I scrub the timeline, you can see that all the timing is offset. And they're looping because I have the looping behavior configured. So if I were to go back to this fall off and let's say add some noise, and I can, maybe I can crank the amplitude of that a bit. Now you can see that these guys are like slightly offset within each row, and I can drive that even further if I need like a lot more noise. I can, remap this so that it's a lot stronger in certain areas. Let's try output min of like many more frames, max, or I could use a noise fall off. It's kind of up to you. But you can get a lot of variation from this for cheap. All you have to do is compute a point attribute. It doesn't matter what it is. For example, I could just say in a point wrangle, if I just wanted to completely randomize this using VEX instead of a fall off, I could say, let's say offset equals fit01. Sorry about the VEX if you're not really a VEX person yet, but I'm just going to generate a random number based on the point number. That generates a number between 0 and 1, which is what fit01 is meant to work with. So I'm going to set the offset to be a random number anywhere between 0 and the full length of the sequence, 26. So now I have a point, or the attribute called offset that's just completely random between those two numbers. I'm going to set the attribute name to offset to match. And now each of these guys is completely random in the sequence as they're walking. So this, again, it's a way to just sort of open up your ability to define the timing exactly for each one of these things. Just let me look at it real quick. Yeah, that's as far as I'm going to go with this specific demo. The one thing that I want to point out here is that Houdini's viewport, when dealing with time offset sequences like this, is very fussy, and it will not. It will sometimes lie to you. Especially when you're doing time offset sequences like this, and you have a lot of objects, you might see things start to run in lockstep, even though you don't have them configured that way. The first thing to check is, again, to make sure that you have these overrides set. If you're not working with packed disk sequences, you need to enable those. But the other thing that you can do, assuming that your sim isn't too busy, is unpack to check. And unpack will always give you the right answer. So if things aren't looking right, isolate a small part of your scene and test with an unpack just to make sure. But the reason why you want to leave these things packed, except for testing, is watch how slow it is for me to scrub the timeline when I've got these guys unpacked versus a bunch of sequences that I can stream in from disk, and I can almost play this in real time. Yeah, Redshift has a packed proxy SOP as well that you can load. And if I were to pull in, I don't know if I have a RS proxy like ready to go here, but this file actually sets the same instance file attribute. So if you bring in a Redshift packed proxy, load in a sequence, and then copy this to points or use the MOPs instancer with it, you can pipe this directly into set sequence time and it'll work like you'd expect. The one downer to this is that when you're using this workflow, it can be, especially if you're time offsetting things, the viewport will lie to you. And there's no easy way to tell what the timings are going to be on them until you render in Redshift. Just as a caveat, whatever Redshift is doing to load that instance data at this point in your SOP graph, even if you change the timings later by modifying the instance file point attribute, the viewport won't reflect that. So keep that in mind for Redshift specifically when you're using the instance file workflow with Redshift with this SOP. You're not going to be able to see the time offsets in the viewport, but it will render. Okay, let's go on to the next section. It's just going to take me 1 second to load this up. Okay, there's two really important parts of transforming things in MOPs that I've kind of glossed over before, but I want to go over them in a little bit more detail. And that's the MOPs pivot modifier and the MOPs reorient modifier. You might have also seen MOPs align early on. They essentially mean the same thing. MOPs pivot and MOPs align are the same node, just aliases of each other. But what this lets you do is adjust the pivot points of your geometry in a way that's a little bit easier than trying to do it just with the intrinsics. So let's do a quick pivot demo. I'm going to make a pol and a grid. And same as before, I'm going to use Orient Mesh to just get myself like decent starting attributes for this. I'm going to turn off auto up and then copy to points. And let's make sure we're instancing for this one. Grab the first output of the test geometry so that I get this field of pols. So the next thing that I want to do is just drop down a transform modifier. So by default in Houdini, when I'm packing things, it's going to pack at either the centroid or the origin. And that can be problematic when you want things to be stuck to the floor or you want to be specific about where that pivot is because you don't, it's kind of option A or option B. And so a lot of the time when you run into issues with pivots and the copy SOP, you kind of have to put a transform in before your copy to points to like nudge your geometry around. And it can be tricky to do it because you're not always in the right space. You have to start like kind of looking at things backwards to make the pivots line up. So as an example, if I scale everybody down by 50% here, you can see that they're hovering well over the ground just because of where they're packed. As an alternative, if I put down a MOPs pivot here upstream, I can say align to bounding box -y. And now these guys are going to scale. I can just toggle this on and off. You can see that now they're scaling from their own local -y. And you could have this working on any side of the bounding box. So I could adjust him any way I like using these quick controls. And this is just for bounding box alignment. There's a lot more options I can show you. But what this means is that all transformations are going to happen relative to -y. And that's not just for scaling, it's for rotations as well. So if I rotate on X, you can see that he's rotating at the point between his feet according to the sort of the center of the bounding box at the minimum Y. That's what this quick control here means. It's like it wants to align to one center of the bounding box or the center on two axes, and then either the minimum or the maximum on the alignment side that you choose here. As another quick example, sorry, just 1 second. I'm going to drop down a box, put some normals on it, and then let's just do a quick instancer. I'm going to set up a 5x5 cube. So I'm going to change this to fixed number, just 555, increase the distance a bit. There we go. So now I've got this cube here. And I just want to show you what, just a little bit more about how you can sort of think about pivots using MOPs. So I'll put down another transform modifier here and just have all these guys spin, let's do frame times 5. So you know this from the first MOPs lesson, but when MOPs applies transforms to things, it's applying them to each point individually, right? So every one of these is going to be rotating around its own local center, or depending on where that pivot is. instead of the transform SOP where it would treat everything as the same. But we can do the same thing with MOPs and actually keep it loose and be able to change this after effect by using pivot at multiple times in the stream here. So what I can do is just, I don't want to do center pivot. What I do want to do is set the pivot in world space. There's a lot of different options that you have here. By default, you have center pivot and you have aligned to bounding box are really simple ones. But you can also dial in exactly how you want to shift the pivot, or you can set the pivot per object in either local or world space. If I set the pivot to be 0 in world space, and then apply the MOPs transform modifier, and this might be a little easier to see what is happening to the pivots when I run this. If I delete geometry but keep the points, you can see that all of the points now are, you can't really see through that nomen, but they're all at 0. Everything is at the origin 100%. What MOPs pivot does is it adjusts those pivots after the fact, but it keeps the geometry in the same place. So that means that future transforms are going to be done around that pivot per object. So now that I have this pivot defined here, if I go back to my transform modifier, every object is pivoting around the same location. And so now it's acting as a single block when I transform it. And you could, in theory, if you wanted to animate these in order to mess things up, get a little stranger with it. I'll show you real quick what I mean. Let's do a box and a tube. And I'm going to set the box to be, leave it alone, but add vertex normals. And then this tube, I'm going to set to be oriented to Z. I'm going to give him end caps. And I want to make it less of a tube and more like a hexagon. So let's just turn the columns down to 6. Let's move him off center so he's not right on top of that box. There we go. I'm going to merge these guys together. So what I'm going to do is roll these guys around, and I'll show you what that looks. What I want to show you is how you can use pivots to dynamically adjust over time where things are moving, so that you can, for example, have things stuck to the ground. So I'm going to do a MOPs convert to turn both of these guys into packed primitives. So that's already ready to go. And now what I'm going to do is give each of these guys like a walk cycle. It sounds weird, but what I'm just going to really quickly use a transform modifier to just set like a quick and dirty rotation. So starting at frame 1, I'm going to key rotate Z, and then let's do like frame 8. I'm going to have it rotate 90 degrees. And I did this after the merge. I do want to apply this just to the cube because each of these guys is going to need to have a separate walk cycle, right? A separate roll cycle. So I'm setting the group to be 0, so it's only affecting the cube. And then I'm going to just add a break in here, maybe. Yeah, let's just step in there. And then set another key. And then from here to, let's say, 28, I'm going to rotate to 180 degrees. So I'm just doing 2 little quick steps so you can see what this looks like. So 1, 2. And then let's do another one for the tube this time. And I'm going to start him same way at, I'm going to rotate over the first 8 or so frames. And again, I want to set this to be primitive 1. So I'm just using this to quickly grab the group masks, and I'm only transforming this guy. So let's set this to 60 because this guy has 6 sides. So he's going to rotate by 60 degrees per side. So now I have a 1 turn, and let's just do a break. And then, same deal. We'll start around here, and then right around this point, we'll do 120. So real boring, right? But what I can do with this is with MOPs pivot. And if you've ever watched any of the MOPs Plus tutorials, there's a little animation that I do that's kind of following the same principle of like that little cube that dances around to that stupid song. What I can do is I can say align to bbox -y, but I can turn off pivots only. And so what this means is that instead of adjusting just the pivot point at which this thing moves, it's going to move the entire primitive according to the pivot shift that we've set. So if I turn this off, now you can see that these guys are suddenly aligning themselves to the ground to -y, but the primitives are moving. So if I have these guys sort of centered over something and rotating around on like a ground plane or on some other arbitrary object, I can use this to lock them in place. So now, because this pivot shift is happening after the transform, it's going to pay attention to rotations. So as that square rotates, you can see that he's sticking to the ground and then snapping back down again. Right? Now, this guy isn't working well because, as it turns out, the way that it's doing the bounding box calculations is by a very sort of loose bounding box that's according to the packed primitive as like an imaginary cube instead of actually paying attention to the shape of the object. If you turn on accurate bounds, it's going to be a slower process, but now you can see that this guy is accurately pivoting off of each of those sides as it rotates. So there's a lot of unexpected stuff that you can do with MOPs pivot that you wouldn't really think of. Stuff like this that can make it a lot easier to get more interesting animation without having to constantly counter animate to get things to fit, which I'm sure some of you guys have run into before. I just want to do one more example as far as like really weird behavior that you can get out of this, because adjusting pivot points can be really strange. I'm just going to make another cube, scale them down a bit, get vertex normals, and then drop down another instancer. I'm going to do another, let's do another fixed grid. Let's do like a 5x5, crank the distance up a bit so we can get these guys away from each other. And then I'm going to do a MOPs pivot. And what I want to do with this is shift the pivots, but I'm going to do it using a VEX expression. So apologies for the VEX here, but I'm going to turn on shift pivot mode. And what this means is that it's going to be, and you can see when I move it along Y, you can see the pivot points raising up into the air. What I'm going to do is use an expression to sort of just animate this over time in a weird way. So I'm going to create a temporary attribute I'm calling Y. And I'm just going to say this is equal to the sine of time plus the point number, and then multiply that by 4. So it's going to generate a value between, well, you'll see what I mean, but it's going to generate a value between -1 and 1 at a given frequency, and it's going to be offset by the point number. So each point is going to evaluate slightly differently. And now I can just say pivot.y is equal to that temporary variable I just created. And so if you can see that if I scrub the timeline that the pivots are just dancing around up and down. But any future transform that I do with MOPs is going to be paying attention to those pivots. So I can just set a simple transform, like let's say rotate by frame times 10. So really simple transformation, but because of the pivot animation that I've done upstream, I can get sort of really weird and complicated behavior out of this for cheap. And this is, these are simple expressions. I could modulate this a lot more to get like really chaotic behavior out of these things without that many keyframes. The next thing I want to go over is MOPs reorient, which is another tool node that has a few very specific use cases, but it's really handy for doing to the orientation of a transform matrix what pivot does, what MOPs pivot does to the pivot point of each packed primitive. So to show you what I mean, I'm going to start with the old pig head and then another instancer, just making copies of stuff. And I'm just gonna turn down the scale of these guys and then zoom in so I can see it a little bit more clearly. Yeah, there we go. And then really quickly, I'm just gonna randomize the orientation. So I've got this grid of pig heads and they've all got completely random orients. What MOPs reorient lets you do is basically tell future MOPs operators what you want the axes of rotation to be. And it lets you do that without having to unpack the primitive. So it's sort of applying a pre-transform attribute to your points And then future MOPs nodes will read that and say, oh, okay, those are the rotation axes that I should be using instead. But it lets you do this without unpacking, which is a big deal, because otherwise the transform intrinsics are what they are. And if you want to rotate locally around other axes later, you have no way of controlling that with vanilla Houdini, unless you want to get really weird with the math under the hood. So to demonstrate this, if I'm doing, let's say, a MOPs transform, and I want these guys to just be doing the usual, the same spinneroonie demo I do every time. So frame times 5 in Y. By default, these guys are all going to be rotating along their own local axes, right? So they're going to be spinning randomly. But if I want that spin axis to be something more specific, but I don't actually want to rotate the objects to get there, that's where MOPs reorient comes into play. So let's drop down a MOPs reorient before this transform. What it's going to be looking for as the object it wants to deal with is two things. The orient source can either be a point attribute or it can be a reference geometry. And I'll show you what the reference geometry thing means in a second. But with point attribute, what I can do is either feed it a quaternion attribute, which is how orient, it's like a 4-dimensional vector, which is how orient usually works. If you look in a spreadsheet, it's 4 numbers. They're incomprehensible. Don't bother trying to understand what they mean. Or you can use 2 vectors. So you can provide an n and an up attribute, or you could provide a matrix attribute. It's up to you how you want to set it up. What I'm going to do is upstream of this, I'm just going to create a new orient attribute. And it doesn't have to be named orient, it can be whatever you want. But I'm going to say orient is equal to 0001. I happen to know that this is the identity orientation. This just means default Z faces Z, Y face, up faces Y. You know, it's like it's a pass through. It means no transformation. So I'm going to set this and then tell MOPs orient or MOPs reorient that I want to use that attribute to define my new axes of rotation. Now, when I run the MOPs transform modifier, I'm still in local space, and these guys are still all scrambled around here. But when I do the spin, they're all going to be rotating along the same axis, and that's the one that I defined up above. So any future MOPs operator that I use here is going to treat this as the starting orientation, or treat this number, this 0001 as the starting orientation. So it's a pre-transform almost. I hope I'm explaining this clearly. But this means that it's new local axes. If I do a visualize frame, hopefully this visualizer will work, you can see that without the reorient, the blue axis, the forward axis is pointing, according to each pig head. But when I turn this on, you can see that MOPs visualize frame is saying, oh, okay, these things are all completely facing the same direction based on those rotation axes that I set. And you can see that they're spinning along with it. The advantage being that if you wanted to do this using native Houdini tools, you would probably have to unpack, or you'd have to compute this offset yourself and then repack after the fact, after you've done your randomization. So another real quick example, I'm just going to grab these two guys here, copy this setup. And I'm going to use attribute randomize. And let's just say I'm going to make something called my orient and set it to be 4-dimensional direction or orientation. So doing exactly the same thing really is as what MOPs randomize is doing, but I'm not applying this to these objects. So everything here, I've got this, I could even call this orient if I wanted to, but all these guys are still aligned completely forward. And now I'm going to use MOPs reorient to use that attribute, my orient, as the new axis of rotation. And now I'll just grab this same transform modifier I had before that's spinning over time and wire it in here. And I'm more or less doing the opposite of what I did before. I have all these guys lined up. They look like they're straight. And I'm doing a simple transformation along local Y, but now I've scrambled local Y so that it's different for each one of these instances. And so now you can see that they're all rotating differently. So you have total control over the rotation axes of each of these things, basically however you want to set it up. So to go back to the orient source mode, the reference geometry mode, this is for situations where you want to align your packed primitives or packed fragments or whatever they are to some other geometry, like a reference mesh that has the orientation that you want. So for example, I have a sphere here. I'm going to orient the mesh so that I have an orientation to transfer to. And I'll just do the usual, you know what, I'll just leave on auto up, it's fine. I just want to have some orientation to begin with. And now I'm going to scatter some points on this. Say, I don't want 1,000, let's do 100, and then shatter it. Okay, turn on wireframes so I can see this a little bit better. Okay, so now I have this shattered geometry. I'm going to run this through MOPs convert to turn it into packed fragments. Now, if I run a MOPs transform on this to move things outwards, the problem is that because I'm using MOPs convert on a bunch of stuff that's been scattered, they have no implicit idea of what orientation means. They don't know what forward or out is. So if I translate these guys in Z, they're all going to move in the same direction just because of how they were created. They don't have implicit transforms. They're just saying like, oh, okay, X is X, Y is Y, Z is Z. With MOPs reorient, what I can do is take the orientation of that original sphere object, wire that in as the second input. So I'm going to grab the output of MOPs orient mesh here and apply that here. And then I'm going to change this from point attribute to reference geometry. Now this has an orient attribute from MOPs orient mesh. It also has n up. So you could use either one, like the attribute type controls are still exposed to you. But what it's essentially going to do now is transfer the orientation of of the original mesh to these packed chunks. So if I do this before the transform, let me reorder this a bit. Now when I move outwards, it's actually using the reference orientation of that mesh to do it. So now I've got these things exploding outwards. This can be really powerful when you're trying to do things like MOPs explode actually does this implicitly. When you explode a mesh, it's using MOPs reorient under the hood to configure those chunks so that everything's local transform is facing the right way. But this is a really powerful way of being able to have like simpler control over what you're doing under the hood with these objects. And just really quickly as sort of a last demo of this, I'm just going to move these points outwards a bit. Let's say that, so the MOPs orient attribute, which is what's created by MOPs reorient here. And you can see if I go over here, there's this special attribute called MOPs orient, which is another quaternion, just like regular orient, but it's sort of an offset that's calculated and then applied to the orientation of every other MOPs operation before it runs. This is one of the few attributes that has nothing to do with vanilla Houdini and doesn't translate to anything. So if you know that you've got, for example, I've got all of these guys randomly rotating because the local axes of orientation are all different. If I want to get the transform of these objects in world space, I can't just read the intrinsic like I normally would. So as an example, I'm going to use extract attributes, which is I'll go into this more in a bit, which is going to pull the transform intrinsics and turn those back into point attributes. If I then take a rubber toy, and let's just match size it, and then copy that to these same points as the original objects that I had. So here's A and here's B, and I'm gonna scale this guy way down. Oop, I have to do that after the fact because I'm scaling to fit. Let's just do it this way. Let's make sure I'm good. Oh, it's because, oh yeah, I did this on the wrong example. Let me just do that from this one. Oh, that's very interesting. I don't know why this is working. It's supposed to not work. The point that I'm trying to make is that MOPs orient is not native. And so if you were to try to just grab the transform intrinsics as they are and apply them to new objects by just copying to the same points, you want to make sure that extract MOPs orient is enabled in most of those cases, because what you want to be able to do is make it so that, in fact, I wonder if this is a bug and I just need to reverse that toggle for this example, because, yeah. Oh, I see. Yeah, it just needs to be flipped. But with extract MOPs orient on, what this means is it's going to apply that pre-transform as part of the computed orientation. So you can see that now these guys, the rubber toys, are being oriented as if the MOPs reorient up the chain. I have these guys spinning along Y, right? Even though their orientations are all completely randomized. So this is not a bug. This is just me getting confused because I need more coffee. If I copy these guys to these points and I don't extract MOPs orient, what it's going to do is apply the exact world rotation of each of these things as they are to those individual points. But that's not taken into account that these guys' orientation axes are actually facing straight up because of the orientation change that I made earlier. So with extract orient on, what it's going to do is apply that pre-transform to the template point attributes that this node creates, so that now these guys are all facing the same imaginary orientations that we made with MOPs reorient. I'm sorry for the confusion. I hope that this makes sense after the fact. That's what this flag is for when you're dealing with orientations that are generated by MOPs reorient. I hope that makes sense. Okay. Just give me 1 second to open up the next file. So speaking of extract attributes, I want to talk really quickly about the API nodes that are sort of the core of what goes on within MOPs under the hood. And there's two main API nodes that are involved in MOPs, and you'll find them in almost every node inside MOPs if you dive inside any of the nodes, and I encourage you to do so. But the two nodes that you're going to be working with are called apply attributes and extract attributes. We'll talk about extract first because it's super simple. I'm just going to create let's do we're running low on time, so I might just copy this network over just to make it easier for you and then step through just for this example really quick. So what I'm doing is starting with a pig head and then instancing it into a grid and then randomizing a bunch of stuff. So the same sort of demo I've done many, many times where I'm just instancing things and then randomizing what's going on with them. And then I'm going to rotate these guys slowly over time. So these are similar tricks that I've done a million times already. And then what I'm going to do is run extract attributes. What extract attributes does is it takes these transform intrinsics, all these secrets in here and the pivot intrinsic and all these other things that are applied to each one of these objects, whether or not you use them with MOPs, it doesn't care. And it's going to turn those back into template point attributes. So this is sort of the translator to take the packed data that lives inside every packed primitive and turn it back into template point attributes like scale, up, n, orient, all of that stuff. What that allows you to do is then go back to copy the points after the fact. Like now I have this rubber toy. I'm going to match size so that it's a unit scale and then copy to points. And so if I toggle from A to B, and this might be a little bit hard to see, these guys are all oriented and scaled the same way as their rubber toy predecessors. Just template that. So you can see that all these guys are facing exactly the same way. And the whole point of extract attributes, and it's a pretty simple node to use, is to just make sure that you can translate from the intrinsics to template point attributes and then use that to do other calculations later on the points where MOPs likes to work. Another thing that I want to point out, and again, I'm going to, just because I don't want to bog us down with too much stuff that we don't need to go over twice. I have another quick setup here, and this is inside the HIP file that I uploaded inside 102.zip. This is part of API nodes.hip. What I'm doing here, just to step through this really quickly, turn off the templating flag. I've got this pig head here, I'm going to move it upwards and then turn it into a volume, scatter points, and shatter it. This is a workflow that you guys should probably be familiar with. It's a really easy way to shatter geometry. So now this guy is fractured into a bunch of different points. So I can run a MOPs convert to turn this into packed primitives and then run it through a simple bullet solver. So all I'm doing is putting this through the RBD bullet solver and then just run the simulation for a few frames. So it's just crumbling. There's no constraints. There's nothing other than gravity and a ground plane. It's all very simple. On the other side, what I'm doing here is running a subdivide. And then basically I'm just adding a bunch of noise and like making these things more complicated. So now I have this super, this is my high res geometry. So what I can do is take the results of this bullet simulation, because bullet is just working on packed primitive intrinsics, the same as anything else. I can extract those attributes and then apply them, which I'm going to get to in more detail in a second, to that high-res geometry. So it's a little bit like the transform pieces SOP, but what I'm doing is taking those intrinsic values and then just assigning them to this high-res geometry, which is also packed primitives. And so now I'm getting this high-res geometry being run through this simulation. Very similar to transform pieces, but I'll show you next in detail sort of what apply attributes can do, because it's a very powerful node. Okay, so now we're going to go on to apply, which is where things can get really interesting. Make a new geometry container. So apply attributes is the node in MOPs. It's responsible for most of what MOPs can do. I'm going to drop down a grid and then use an add SOP to just turn this into points. And then let's make a pig head and copy to points. Make sure we're packing. And then just scale this guy down a bit. Okay. So what I'm going to do now is mess with some template point attributes on these original points here. So I'm going to hang on to these as sort of a separate stream. I have my packed information here, exactly 100 packed primitives, and I have my points here. And I've already copied these to points. So these intrinsics are set. But what I can do is let's drop down attribute noise and have it affect P. So I don't really need to be too specific with this. I guess I'll zero center it. But yeah, I won't change anything else. So I'm sort of scrambling P. And let's do the same thing to N and up, because we're not locked to just working with the orient attribute. If it's easier for you to think about it this way, we can use N and up as well, because all of these are supported. So I'm going to adjust the N vector. And I'm just going to adjust with random. So I'm going to get a random N for each one of these guys. And then I'm just going to copy this and paste it. I'm going to do the same thing to randomize the up vector. And then I'm just going to tweak the seed so I know it's not the same. And then I can do another one of these for scale. So I'm going to change this to scale. And then let's do adjustment for length only, because this is not a direction vector. And then again, I'll randomly adjust it between 0.5 and 1 for each one of these things. So now I have all these randomized template point attributes. And again, I have all of these guys as packed primitives ready to go. Now I'm going to use apply attributes. So the template points, the points that have the attributes that I want to match, go on the right side, and then the objects I want to modify go on the left. And when I turn on the display flag, what's happening is all of those template point attributes that I set. So basically the same way that we use the copy SOP, I have all of these template point attributes set up. But what apply attributes is doing is then using those attributes and modifying the transform intrinsics to match. Which, if you already know a little bit about VEX, so the copy SOP is pretty straightforward. But the power in this is that you have a lot of options for how you want to do this application. So the most obvious thing that you can do that apply attributes does, and this is why it's the center of almost everything that MOPs does, is it pays attention to fall off. So if I have a plain fall off here and I just slide this back and forth, it's going to interpolate between these two values. And this is how, you know, the transform modifier works. This is how the move along spline works. All of these things are using apply attributes to basically take some value that we've set and either, you know, set or add or multiply based on these modes to the intrinsics under the hood. As another quick example, let's do the same thing. I'm just going to copy this here, this initial setup, and then paste it. And I'm going to do a transform modifier on these guys here. And let's just, let's rotate this guy, these all by 90 degrees. They're all facing to the right. I can also, I can apply, let's say, the same transform to these points. And like, you're not going to be able to see this, but I'm rotating all of the points in the same direction. If I then use apply attributes down here, by default, all of these guys are going to be facing that same 90 degrees because that's the rotation that I applied to these, you know, to these template points. But I don't only have the ability to set, I can also add. And if I turn on add, it means that these rotations are going to be accumulated. So now I'm doing two 90-degree rotations, one from this, so I'm already facing this way. And then I'm taking this 90-degree rotation as well on these points and applying it additively. And again, fall off is the same way. I can put down a plain fall off or some other noise fall off here and then interpolate to blend between the two. So the power behind this is that you can use this to sort of, if you know how to set up the template attributes the way that you want, you can use this to create your own sort of mini MOPs operators or your own fully fledged HDAs if you want. These API nodes are both for my own sanity so that when I'm doing these transformations, I don't have to think about the math every single time, but they're also exposed so that you got that, that any technical artist can go in here and mess around and use them to create new effects. The last thing that I want to bring up, and this is a bit overkill, but let's say I have a template head here and I want to zoom in really quick, and I'm just going to apply similar attribute noise to the point position. That's excessive, so let's turn that strength way down and turn the element size way down. But what I want to do is just kind of mess this guy up a little bit. And then I'm going to do a shape fall off on these points. Let's just auto fit, preview. Sure, that's fine. Yeah, maybe let's invert it so that it's more powerful at the top than at the bottom. I can use apply attributes almost like a blend shape. So, but a weighted blend shape. So now based on where the position of the fall off is, because apply attributes is modifying template point attributes, but that includes P. So if I then go into this fall off and animate it, I can get a weighted blend shape based on that fall off value. And I don't necessarily recommend using it this way because it's not going to be as fast as doing like a basic VEX transformation. But if you just really need a quick and dirty weighted blend shape, you can do it this way for cheap. I'm going to open the file for the next section, and I need just 1 minute before I keep going. Okay. So what I want to talk about, and I'm going to try not to get bogged down in the details, is I want to talk a little bit about how you can use MOPs for things that are not motion graphics specific. There's a number of different ways that MOPs can interface with simulations or with, sorry, I think, did I crash? Am I still here? Okay. Sorry about that, just running into a bit of glitchiness here. But you can use MOPs in a lot of different places that you wouldn't normally think of as motion graphics tools. So as a really quick example, and again, in the interest of time, I'm going to be sort of copy pasting some of these setups to make them a little bit quicker instead of building them node by node. And I apologize for that, but I'm hoping that the basic stuff we've already gone over, so I won't waste your time with it. So what I'm doing here is I am taking a template head and filling it at the bottom here and then fracturing it, converting it, and then running a spread falloff. So it's stuff that you guys should probably already be familiar with. I'm generating a bunch of packed fragments here, and then I'm going to run a spread. Because these are packed fragments, you're not going to be able to clearly see the spread animation because you can't preview falloff. You can't set point color individually on packed fragments. So when I preview, I have it set to be display to sprites. And now when I animate, you can see sort of how the spread is working. So I'm going bottom to top using a spread falloff. I'm just going to turn off falloff preview so I get my original chunks back here. And now what I want to do is I'm going to use this falloff value to drive how the simulation runs. And this will seem pretty obvious to those of you who have done like a fair amount of RBD sims before. But in this point wrangle, what I'm going to do is I'm going to modify the active attribute, which is something that in RBD, active defines whether an object is a static collider, meaning it doesn't move, it's just there to collide against other things, or whether physical forces are going to be applied to it. And I'm just going to set this to be, it's going to be equal to MOPs falloff is greater than 0.99. And this might be a little bit confusing if you're not used to writing expressions, but what I'm doing is saying that because active is either 0 or 1, there's no in between. So what I'm saying is if MOPs falloff is nearly 1 or is equal to 1, then active is going to be 1. And so I'm saying I active equals 1. If it's not, it's going to be 0. And so it's going to be static. Now what I can do is run the RBD bullet solver. Sorry, it's just called, yeah, there we go, bullet. And you'll notice that under overwrite attributes, active is already in here by default. And that just means that these objects are going to update this active state from this falloff on every frame, even though it's happening inside a simulation. And so when I play this back, so let's take a second, you see that these chunks are activating and then falling as that spread happens. So you can use this, you can use falloffs to art direct simulations. And obviously active isn't the only attribute you can mess with, but it's a powerful one to know about. And there's others that you can change, including, I mean, animated and deforming are 2 more that you might be used to working with if you know RBD. You could change physical characteristics like mass if you wanted to. You would just have to make sure that it was added to this list for updating. I'm going to add a ground plane and then resimulate a bit. Just go forward a little bit more. Sorry about the simulation wait. I'm sure this is going to get edited out. Okay, so again, we have the spread falloff falling, and as the falloff spreads throughout the sim, the thing crumbles. And let me just run this a little bit further. Not too much further because I don't want to waste anyone's time. But what I want to do is sort of point out a common problem with RBD sims where you might have an object you don't like that's behaving weird, and you want to modify it. So let me just again, in the interest of time, I'm going to copy the RBD settings that I have from the demo file over so that I don't have to, oh boy. You can do it, computer. I believe in you. Come on. Okay, delete this. So now I'm using the same settings because I just, I need to do this quick. What I can do with this now is isolate specific primitives that I might want to adjust the position or the timing of, right? Because again, RBDs are just packed prims. It's all the same at the end of the day. So maybe I want to get a specific object that's like out of control, you know, like this guy here, and I want to slow him down, or I want to, maybe I don't want him to go past this point roughly. So what I can do is I'm going to blast all but this primitive, whatever this number is. Yeah, okay. So delete non-selected, and then time shift him to frame 67. So now what I'm doing is I have these intrinsics from this simulation sort of, what's the word? I have it kind of frozen in time. Like this is the goal position that I want this thing to meet. Now what I'm going to do is run apply attributes. And I'm going to apply it only to that same group, right? So I'm just going to copy this group mask and apply it as the apply attributes group mask. So I'll just paste a relative reference, and that should evaluate to the same primitive. And then plug in the simulation results to part A. And so now what you'll see is that guy is frozen in time at that position that, let's say that this is the position that I want as the final for that piece in the simulation. Now what I can do is just use plain falloff to animate that effect on. So I want him to reach this position roughly, like let's say we'll start here. I'm going to set the falloff value to 0 and start it here. And then by that end frame that we chose, I'm just going to fade this transform in. And this is not going to look very good. It's going to require some tuning to run. But now you can see the whole sim runs. I don't have to resimulate. That's already done. But now I can blend that transform in. And so this guy sort of comes to a stop where I need him to stop. And this can apply to particle simulations too, if you want, but it's especially prevalent when you're dealing with RBDs because you have all these individual objects with packed transforms that if you've dealt with bullet simulations before, you frequently have, you know, 1 or 2 objects that are just going to freak out, spin around indefinitely, just do other weird stuff. And this is one way of making corrections to that without having to resimulate, which can be really frustrating and take a long time. Okay. The second part that I want to show you is about how you can use some of these controls with Vellum, because that's obviously a really popular solver right now. It's really cool. It's fast. You get interesting results from it. So if you're not familiar with Vellum, I'm going to step through this quickly, but I want to just make sure that you know each part of this process going in. So I'm starting with just the same template head that I usually work with, and I'm going to make a Vellum cloth. So Vellum configure cloth and pipe the geometry in. And this is going to build just sort of a basic list of constraints to make this thing stick together. It's nothing fancy at all. What I'm going to do next is drop down a pin constraint. So where is that pin to geometry? Well, I'll just drop down another Vellum constraints and then set the preset. So I'm going to set this to be pin to target. And I wire both of these things in because I have the geometry stream and the constraint stream. I need them to pass through. And what I'm going to do with this pin to target constraint is I'm going to set it to be soft constraints. So under pin type, I'm going to set it to soft. And this means that I can set a value between 0 and 1 on each of these pin constraints to tell them how tightly do I want these constraints to bind to the original geometry to keep it stuck there. It's almost like a goal to the original geometry that I'm pinning to. And the other thing that I want to do to make this work is I want to set an output group for these constraints, for the stretch constraints involved here, and I'm going to call this pin. And this is so I can target these constraints specifically later on. All the rest of this I can leave as default. So what I want to do with this is I'm going to use falloffs to modulate constraint properties so that I can have things change over time in the simulation without having to get to individually address nodes another way. The first thing that I need to do, and this is confusing, but when you're using the Vellum solver SOP, the order of the constraints isn't guaranteed. Houdini can scramble your constraint order. And so the first thing that I need to do is I need to set some kind of ID or index attribute on my constraints so that I can refer to them by name later. So I'm just going to call this ID and set it to be as a primitive attribute. So now each of my constraint primitives have a unique ID attribute. I'm going to need to access that later. And that's just because you can't trust the Vellum solver SOP to keep your constraints ordered. The next thing that I'm going to do is create a shaped falloff. And what I want to do is basically have this falloff sweep over the geometry from one side to the other. And this is going to control the strength of the pins. So I'm going to start like maybe a second in to the animation, and I am going to, let's see, let's move it this way and then rotate it 90 degrees. I'm going to turn on preview fall off. I want to scale it down in Z so that the contrast is a little higher. And I think I actually want this to be rotated -90. So now when I animate it, it's going to sweep from one side to the other. So I'll start here and then keyframe translate. And then over about a second, I'm going to sweep it across. And I might even narrow this more. Maybe it can be a little bit smaller than this so that the transition is a little bit more drastic. Yeah, so I'm going to have like this, this area sweeping over, and this is going to be used to directly affect the constraint strength. So the next thing I need to do is, because constraint properties are primitive attributes, they're not point attributes, I need to use attribute promote to promote MOPs fall off from a point attribute, which it always is by default, to a primitive attribute. So I'm just going to grab MOPs fall off here, and now it's promoted to the primitives. And finally, what I'm going to do just to make my life a little bit easier is I'm going to flag this with a null and just call this constraints. Lastly, I'm going to drop down the vellum solver SOP, which is right here. And the geometry goes in the first input and the constraints go into the second. And it's already trying to simulate, which is why it's taking a little bit of time. And you can see that starting out, because these pins have a constraint weight of 1, nothing is happening in the simulation because those pins are active from the start. So what I want to do now is go inside the vellum solver and use this fall off to directly modulate those constraint values. So if I dive inside the vellum solver, one of the ways anyways that you can quickly mess with constraint properties is using the vellum constraint properties DOP. And I'm just going to wire this into the forces tab. What I want to do is first I want to go to the inputs tab, and this is important. I need to be able to read from that constraints null that I built because that's where the attributes are changing over time. That's important. So for input 3, I'm just going to change this to SOP, and then I'm going to point it to that constraints null that I set. So now I have this as input 3, and this is necessary so that I can run a VEX snippet on it. So I have an address that I can reach it at. Once that's done, I'm going to go back to properties. And if I run this function without setting a group, it's going to modulate every single constraint on the entire cloth object. And that's not what I want. I only want to affect the pins, because if I affect everything, then this is just going to turn into soup. So I'm going to set this to be the pin group, and that's the group that I set earlier in SOPs on these pins specifically. And what I want to do is adjust the stiffness. And so right now this is just set to 1. But what I can do is use a tiny little bit of VEX to adjust this after the fact. So I'm going to turn on use VEXpression. And then what I want to do is grab the original stiffness of the constraints moving in. So what I can do is just say float. I'm just going to call this original stiffness is equal to the primitive value of those source constraints. So that's input 2. I'm going to get the stiffness attribute, which is whatever it was going in. I think by default, it's like 1 or 0.1. It's something pretty small. And then the ID attribute. And this is the ID attribute that I created on those primitives because this vellum constraint property DOP is running per primitive. So I can use this to address them. The reason I can't use primnum is, again, because those values get scrambled in this SOP and you can't trust them. Next thing I'm going to do is grab the falloff attribute from those same constraint primitives. So falloff is equal to prim2. The attribute name is mops falloff, and I want to grab this again from the same matching primitive by ID. And now what I can do is I want to output a stiffness value that's modulated by this falloff. And so the parameter name here is stiffness. If you hover over it, that's how you know. And so what I'm going to do is say stiffness, this is going to be the override, is equal to that original stiffness that I defined. So orig stiffness times falloff value that I computed. And now I'm going to jump back out. And the last thing I want to do is just make sure that my shape falloff values are sane, because pins are really sensitive. And I don't necessarily want any pins to be like 100%, or the points are just going to snap back when the constraint rolls through them. So I'm going to go back to my shape fall off and just set the remap so that the maximum value of any pin is 0.1. Okay, now that that's done, what I can do is play back the simulation. And initially, oh, I need a ground plane, I'm sorry. Let's go in here, and I think that's under. There we go, ground position, check that on. And so now initially the whole thing is going to collapse because there's no pins involved. It's just the cloth constraints that are holding it up. But starting a second in, as that fall off sweeps across, it's going to activate those pins. And we could even use smaller values for the pin constraint if we want the rise back up to be a little bit more subtle. We might need more sub steps to really dial this in. But you can see that it kind of springs back this way. I could even have this output max be even lower and see if this works better for modulating those constraint primitives. Let's try that. Yeah, so there's a little bit more bounce the second time in when working with this. And if you want to play with these physical settings, again, this is in the HIP file for this class. It's under 05 simulations.hip. But you can see that you could use this fall off value in similar expressions to modulate any part of a constraint. That's, that includes stiffness, but you could also do this to apply to rest length, for example, which is another really fun one to play with. You can get some really weird growing bulging effects from that. But the point is to just, MOPs is creating attributes, and everything in Houdini is about attributes. So if it's easier for you to art direct these things using simple, spread fall offs or shape fall offs or whatever you've got to get the point attributes that you want, you have them at your disposal. They're easy to loop. They have built-in noise. So you can kind of just use these to drive other parameters in simulations without having to think too hard. Okay, the last section I want to go into is just a pretty quick one about common mistakes with MOPs, easy places to get tripped up. This will just take me 1 second to load the file. I'm going to create a new scene here. So the first thing that I want to talk about is merging geometry streams, because this is a really common one that you'll run into where you merge two object streams together and you don't understand why your stuff isn't working. So really quickly, I'm going to make a box, give it some vertex normals, pipe it into an instancer. Actually, you know what? In the interest of time, we don't really need to do this to describe it. So I'm just going to copy this setup really quick so that we can just go through it node by node. So here I have a box, an instancer, a sphere doing exactly the same thing. I'm transforming this over, and now I'm merging these two areas together. Now I'm putting down a shape fall off that is going across the entire length of this, but you see that gap in the middle? The reason that this is happening, and the reason this can't work as is because if we go to our point attributes list and we look at and we look at our IDs, the boxes here are starting 0 to 24, but so are the spheres. And most MOPs operators are very sensitive to the ID attribute. You need to have a unique ID for everything going in, or else you're going to get inconsistent behavior when you set these things up. So one way to get around this, and there's a number of different ways that you can handle this, is, for example, in this setup, what I could do with these spheres is go to the sorting tab and make sure that my ID start number, it leaves me enough room so that I don't overlap with the box. So I could either set this to, 1,000, and now you can see it works just fine. Or if you want to be procedural about it, I could say endpoints and then path to the MOPs instancer. And now that expression is going to evaluate to exactly 25. So now I'm starting at 25. And so you can see that my IDs are going smoothly when I merge from 0 to 25, and there's no overlaps. And now the rest of them just sort of tack onto there. So that's an easy way to resolve this. If you know that you're going to have multiple MOP streams that you need to merge together, you can just make sure that even going into them, they have different values. Another way that you can get around this, if you don't want to set up that ID start number expression, I'm just going to delete this really quick and go back, is you still have MOPs convert. And you can run this in packed primitives mode. And so I can just say packed primitives and then override the ID attribute and also override name. And now it's going to automatically, again, take the point numbers, regenerate a new ID attribute from that, and then also regenerate a new name attribute if it has to, so that the name attributes also are all unique. The other way that you can get around this is like, I could call the, I could call upstream, I could call the MOPs instancer, I could give it a different name prefix. So these are named sphere instead of just piece. And then if I turn off override name here, now you can see that I'm getting piece 0 through 24 and then sphere 0 through 24. So that's another way to keep these things separate. The name attribute is mostly required for RBD simulations because if two packed primitives have the same name, they'll be solved as the same object. But a lot of MOPs nodes, especially modifiers, have, like if you look at apply attributes or anything that inherits from it, you can see that you have a match by tag here that you can switch from ID to name. There's some situations where you might want to use one over the other. So you have both of those options. And that's why MOPs convert gives you these options as well as the ability to better control packed RBD simulations. Another similar problem that you'll run into occasionally, not as often, is sort order. So if you're in a situation where, you, for whatever reason, you need to randomize the point order of something because it makes it easier for you to dial in some random value later in your project. Really quickly, I just have a Paul here. I'm running him through an instancer to get a grid of Pauls, and then I'm randomizing my point sort value, but I'm not randomizing my primitive value. So what's happening now is that there's a desynchronization between my point values, like my point numbers, and the packed primitives that they represent, because all of these things are done by an ID value, a name, and MOPs by default assumes that your point order is the same as your primitive order, so that if it wants to fetch a packed transform for something on a point, it knows that the point that you're referring to means the same primitive number that you're referring to. If you mess with that sort order, MOPs all of a sudden has no idea what you're dealing with. And so when I apply a shape falloff and then try to transform, even though the shape falloff is linear, it looks random because my sort order is wrong. You can see if I turn off this sort node, these guys are moving in the right order. So to get around this, you have two options. One of them is to just not randomize your sort order and find another way around it, or resort your packed primitives and points after the fact to make sure that they're working the right way. Or there's a infrequently used MOPs node called MOPs sort that does this for you. And you also have the ability to rebuild the ID attribute from the name if that's a better way to get it back. Otherwise, what it's going to do is use the point number to regenerate a new ID, not a new ID, but it's going to resort based on what it thinks is the right order in order to keep your point and your primitive numbers consistent. And so now you can see that with MOP sort in place, the transfer modifier works, and you can go back to what you were doing. Another thing is like, if you're going to merge geometry streams in that aren't using MOPs, and I don't recommend that you do that, you need to make sure that you're doing that at the end of the network, because let's say you have a bunch of loose points or like volumes, or I don't know, people have tried to do some really weird stuff and sent me demo files that don't work. And it's because they're trying to mix and match all of these different things and like splines in the same flow. My advice is to keep those things separate, but if you have to merge them together, do it at the end of the chain after you're done doing all of the MOP stuff. Another really common thing, and I've alluded to this already, but I just want to drive it home one more time, is dealing with packed fragments and falloff preview. Really quickly, I'm just going to paste the network in here. And it's the same sort of fracture setup that I've done before, where you have a test geometry. I'm going to scatter points on it, run it through Voronoi fracture, and then MOPs convert it. So now I have a bunch of packed fragments. If I run a MOP shapes falloff on this, you can see that the shape is covering the whole pig, but the whole thing is equally pink. And this is just a built-in limitation of packed fragments. The viewport cannot display unique colors on them just because of how Houdini is optimizing packed fragments under the hood for display. And if you're curious, packed fragments, you can just look at the middle mouse menu and you'll know that it's a packed fragment because it'll tell you. They're slightly different from packed primitives for optimization reasons. But what you need to do in this case, if you can't get an accurate preview, is just turn on display as sprites and then just adjust the sprite scale to fit. You can even override the scale completely if you need to. And now you can actually get an accurate view of what this is doing. You just want to make sure that when you're done, you turn off display sprites or turn off preview fall off entirely, because you obviously don't want to render these sprites. Another little known thing is that if you have a lot of fall offs down the chain, or like you don't know which fall off has this preview on it that's messing things up, there is I'm going to turn preview fall off back on. There is a little known tool on the MOPs shelf called disable fall off previews. And what this is going to do is crawl your entire SOP chain looking for fall off nodes and disable all of them at the same time. So if you ever get to a point where like you have preview on and it's messing up your color downstream and you don't know why, this will just switch everything off all at once. It's a good one to have in your back pocket in case you get lost, because you can have a lot of different fall off previews potentially enabled in a long network. Just going to jump out again and do another. I got 2 more of these and then we're done. So another thing that I want to bring up is something specific to Houdini 19 and rigid body dynamics that has been kind of a pain when working with MOPs when you're doing dynamics work. And I'll explain what I mean and just paste this in. Again, I don't want to waste anybody's time. So instancing a grid, same thing as always, and then randomizing. So I have an orient attribute that's randomized. If I take this as is and run it through the bullet solver, and this is something that those of you in 18 won't notice, but in Houdini 19, template point attributes like p-scale, orient, scale, there's a few others that it'll consider. On the first frame of simulation in Houdini 19, with packed RBD specifically, Houdini is computing a rest transform based on where your points are at that point in time. From then on, if you have any template point attributes defined on your points, Houdini is going to additively apply those to your transforms. And you can see what I mean here with this randomize. My scale value is 0.18, and I have an orient attribute. On my first frame of simulation, it's scaling everything down by another 0.18, and it's rotating them again because of that orient attribute. And this is inescapable. Like Houdini is going to see these attributes and just do it. And so the way to get around this, if you're working in Houdini 19 and any version beyond that, I assume, unless side effects changes its behavior again, is to put down an attribute delete and delete orient, delete p-scale, delete scale, any other related attributes. And now the first frame of our simulation matches what our randomized looked like. Keep this in your back pocket, because anytime you're using MOPs with RBD simulations, you're going to have to do this every time. I'm hoping that there's eventually a way that I can find to help automate this. But for now, you're going to want to do this before every bullet sim. And the last thing that I want to bring up is something that I alluded to earlier with when I was talking about the instancer. It's really quick. I am going to, again, just paste a quick setup here because I don't really want to go into the details. So I have a DOP network here, and a lot of people want to use the MOPs instancer to copy to particle streams. So I have this particle stream that's just pushing points out, and then there's like a little bit of wind noise to make them swirl upwards. I have 2 objects here, this peg head and this rubber toy. I'm match sizing them and then running them into an instancer. Now, the instancer is set to use, it's in distribution type mesh, it's pointing to that template, and then it's instancing to points. So it's basically acting like a copy to points by default this way. So it's just copying to each of those template points. If I scrub the timeline, you saw how many particles were in that original simulation, right? But now you're just seeing a tiny handful coming up once and then disappearing. This is something that trips people up a lot. The reason that this is happening is because by default, MOPs is assuming that you want to be copying to like a deforming mesh potentially, like something that is animating, like a crag, a test geometry, whatever. And so what it's doing is, in order to save time and also make the instancing solution more consistent from point to point, it's computing computing sort of where the mesh is at the given rest frame, this template rest frame attribute right here, and then applying that, it's sort of interpolating the mesh values from frame to frame after that. It's fast and it's smooth when it works, but when your point count is changing, this method doesn't work. And so anytime you're instancing to something that has a changing point count, you need to take this enable template interpolation flag and turn it off. And right away, now you're going to see that you're getting copies to every single point. This is one of the most common bugs that I run into, aside from people merging geometry streams and wondering why things aren't working. If you're going to use the instancer for this, this is the only way to do it. The other thing that you can do is just use copy to points. Again, MOPs isn't a closed system. There are places where you're going to want to use the instancer, and there's the places where you might want to use copy to points. They're both great for the specific things that they do, but you're not locked to using MOPs nodes in order to use MOPs. You can kind of mix and match as much as you want, as long as you've got an IT attribute. And that's it for this one. I hope that this wasn't too overkill for everybody involved, but I just wanted to get through as much of this system as I possibly could before we start talking about math next week.